Most people imagine danger in the ocean as something that moves toward you with intent, a silhouette accelerating from the blue, a shadow that closes distance, a predator that decides. The box jellyfish breaks that mental model immediately. There is no pursuit, no choice, no targeting. The danger appears the moment a living nervous system drifts into a space it already owns. What makes this animal lethal is not aggression, speed, or size, but the way it hijacks the most basic systems that keep a body functioning at all. Encounters do not unfold as attacks. They unfold as collapses. A swimmer does not lose a fight. Their own nerves, heart, and breathing are overwhelmed in seconds, sometimes before the brain has time to recognize pain as pain. In the water, the box jellyfish barely announces itself. Its bell is nearly transparent, shaped like a faint cube that refracts light rather than reflecting it, dissolving into glare and surface shimmer. In clear tropical shallows, where sunlight fractures into moving patterns, its outline is camouflaged not by color, but by physics. Currents carry it without urgency, its motion dictated by water flow rather than intention. To a swimmer scanning for movement, it does not register as an animal. It registers, if at all, as distortion. The tentacles, however, extend far beyond the visible bell, trailing like invisible fishing lines through the water column, sometimes stretching several meters. These are not passive appendages. They are the weapon system. Each tentacle is lined with thousands of specialized stinging cells, nematocysts, packed so densely that a single brush of skin can trigger an area-wide discharge. Unlike venom delivered through a bite or a puncture, this is contact-based envenomation scaled across space. One touch does not equal one sting. One touch equals hundreds, sometimes thousands, firing simultaneously across whatever surface area they contact. The venom is injected not through a conscious action by the animal, but through mechanical activation at the cellular level. Skin pressure alone is enough. The box jellyfish does not decide to sting. Its biology ensures that contact automatically becomes catastrophe. What the venom targets is what separates this animal from others that simply cause pain or paralysis. The toxins are designed to disrupt ion channels in nerve and heart cells, triggering rapid, uncontrolled signaling. Pain arrives first, but it is not ordinary pain. It is explosive, electrical, overwhelming, spreading faster than the brain can localize or process. At the same time, the venom interferes with cardiac rhythm, causing irregular contractions or outright failure, and it compromises the muscles responsible for breathing. The result is a cascading failure. Intense pain triggers panic. Panic accelerates breathing and heart rate. The venom destabilizes both systems further, and the body spirals inward on itself. This is why survivors often describe the sensation not as being stung, but as being struck from within, as if the body itself turned hostile. The idea that danger increases with contact time is misleading here. A brief brush can be enough. Because the tentacles are long and thin, a swimmer may contact several at once without seeing any of them, creating an instant area effect across limbs, torso, or neck. Unlike animals that deliver venom through a single point, the box jellyfish delivers it across a distributed network. This is why people sometimes collapse without visible wounds or obvious cause, their nervous system already overwhelmed before bystanders understand what happened. The transparency of the animal compounds this effect. Even in shallow water, even on calm days, visibility does not equal safety. Sun glare, surface ripples, and suspended particles can hide an organism that relies on invisibility rather than speed. The danger peaks precisely when humans assume conditions are safest. Calm seas mean box jellyfish are not torn apart by waves and turbulence. Shallow beaches concentrate swimmers into the same warm, protected waters that box jellyfish prefer. Seasonal patterns can increase population density near shorelines, especially during warmer months when currents push them toward beaches rather than out to sea. These are not rare coincidences. They are overlapping preferences between human recreation and jellyfish ecology. The animal is not invading human space. Humans are entering an existing hazard zone that happens to look inviting. What makes the situation worse is the delay in perception. A shark silhouette triggers immediate fear because the brain recognizes a form. A jellyfish does not. Many victims report not realizing anything is wrong until pain detonates, by which point muscle control may already be compromised. Even strong swimmers can lose coordination rapidly as the venom interferes with nerve signaling. In severe cases, collapse occurs in the water itself, turning a toxic encounter into a drowning scenario within moments. This is not because the venom causes unconsciousness immediately in every case, but because the systems required to keep the body upright and breathing become unreliable. Ecologically, the box jellyfish occupies a role that seems disproportionate to its size. It is a highly efficient predator of small fish and planktonic organisms, using its tentacles as a drifting net rather than a pursuit weapon. Its venom evolved not for defense against large animals, but for instant immobilization of fast-moving prey in a three-dimensional environment where escape routes are endless. The same traits that make it effective against fish make it devastating to mammals that lack any evolutionary history with this threat. Humans did not evolve alongside box jellyfish. There is no instinctive avoidance pattern, no built-in recognition of danger. The mismatch is total. The irony is that the box jellyfish does possess a rudimentary sensory system that includes light detection and directional movement. It can orient itself, avoid obstacles, and navigate toward prey-rich environments. But none of that is required for it to be lethal to humans. It does not need to chase, corner, or react. The kill zone exists wherever its tentacles drift. Entering that zone is enough. This flips the typical predator narrative on its head. Survival is not about speed, awareness, or strength. It is about not being there at all. Understanding this animal reframes ocean risk entirely. The danger is not always loud or dramatic. Sometimes it is silent, transparent, and already present, waiting not because it wants to, but because evolution placed it there long before humans arrived. The box jellyfish is not a monster, and it is not malicious. It is a perfectly adapted organism, operating exactly as designed in an environment that rewards efficiency over spectacle. The problem arises only when another nervous system intersects with its invisible machinery. Calling it a jellyfish problem misses the point. This is not about tentacles alone, or venom alone, or even pain alone. It is about how fragile, complex biological systems become when confronted with a toxin designed to dismantle them at the cellular level. The ocean does not always announce its threats. Sometimes it simply waits, clear and calm, while the most dangerous thing in the water remains almost impossible to see. The reef looks open from a distance, a mosaic of color and motion that suggests endless escape routes, but once you drop closer to the substrate, the illusion collapses. What appears spacious from above becomes a maze of fractures, corridors, and dead ends, carved by erosion and reinforced by coral growth. This is where sea snakes operate, not in open water chases or dramatic lunges, but in spaces so tight that speed matters less than geometry. Their world is not the wide blue. It is the crack, the seam, the narrowing passage where prey runs out of options long before it runs out of panic. A sea snake moves through this environment like a living contour line. Its body forms deliberate S-shaped curves that press against rock and coral, allowing it to anchor itself in place while scanning forward. Unlike open water predators that rely on acceleration, sea snakes rely on compression. Every bend in their body stores positional control, letting them hold steady against surge and current while the head advances independently. In tight reef corridors, this matters more than raw speed. Fish that thrive in open water suddenly find themselves in spaces where their greatest advantage, rapid directional change, becomes useless. A corridor that narrows faster than a fish can turn is not just a trap, it is a certainty. The hunt begins quietly, almost invisibly. A sea snake's head moves forward in short, deliberate increments, tongue flicking to sample chemical traces suspended in the water. This sensory system does not provide a picture of the prey, but it gives direction, intensity, proximity. In a reef full of intersecting smells, the snake filters what matters by context. A stressed fish releases different chemical signals than a resting one, and those signals linger in confined spaces. Cracks and rubble act like scent amplifiers, trapping traces that would otherwise dissipate. The snake does not need to see far. It only needs to know which way to go. When the strike happens, it is fast but not reckless. The snake does not lunge its entire body forward. It snaps with the head and neck alone, minimizing the chance of losing leverage. The jaws clamp onto the fish, not to tear or crush, but to hold. There is no prolonged struggle, no wrestling match that risks dislodging the snake from its position. The venom is delivered efficiently, and then the snake waits. This is a critical distinction. Sea snakes do not overpower prey through strength. They let chemistry finish the encounter. The venom is not designed for spectacle. It does not need to incapacitate large mammals or deliver dramatic effects over long periods. Its role is speed and efficiency. Fish are fast, flexible, and capable of explosive escape bursts. To hunt them successfully in confined spaces, a predator must stop movement quickly before a single powerful kick can wedge the prey deeper into the reef or out of reach entirely. Sea snake venom achieves this by interfering with neuromuscular signaling, preventing muscles from responding properly to nerve impulses. The effect is not instant paralysis in a theatrical sense, but rapid loss of coordinated movement. The fish stops being a fluid, reactive body and becomes a drifting object, still alive but no longer capable of escape. This strategy explains why sea snakes hold rather than release after the strike. In open water, releasing prey after envenomation might be viable. In a reef corridor, it would be a mistake. A stunned fish can still drift, and currents can carry it into spaces the snake cannot access. By maintaining contact, the snake ensures that immobilization translates into capture. The body of the snake remains anchored in the corridor, forming a living seal that blocks escape routes while the venom does its work. Once movement fades, swallowing becomes a controlled, almost mechanical process. The advantage of this approach becomes obvious when you consider what other predators cannot do. Larger reef hunters like groupers or moray eels require more space to maneuver. They rely on bursts of speed or powerful jaws, both of which need room. Rubble fields, collapsed coral, and narrow fissures are effectively off-limits to them. Sea snakes, with their narrow heads and laterally compressed bodies, slip into these spaces with ease. They turn structural complexity into opportunity. Where others see obstruction, sea snakes see a hunting ground largely free of competition. This niche specialization shapes their entire physiology. Their lungs extend much farther down the body than those of terrestrial snakes, aiding buoyancy control and oxygen storage. This allows them to remain submerged longer while maneuvering through complex terrain. Some species can also absorb a small amount of oxygen through their skin, supplementing lung breathing and reducing the need for frequent surfacing. In a hunting strategy built around patience and precision, minimizing interruptions matters. Every unnecessary trip to the surface increases exposure and reduces hunting efficiency. Surfacing behavior itself is often misunderstood. When a sea snake rises slowly to the surface, head breaking the water with minimal disturbance, it is not displaying curiosity or docility. It is managing oxygen. The calmness of the motion reflects energy conservation, not temperament. Sudden, splashy surfacing would attract attention from predators and waste energy. A controlled ascent allows the snake to breathe while remaining alert to threats. The snake's apparent indifference to nearby humans during these moments is a byproduct of focus, not friendliness. Its priorities are physiological, not social. Back on the reef, the visual language of the hunt becomes clear once you know what to look for. The S-curves of the body are not random. Each bend is placed to brace against rock or coral, creating a stable platform for the head. The head itself moves with a searching quality, pausing, adjusting, sampling. When prey is detected, the framing tightens. The corridor becomes a tunnel, sealed at one end by rock and at the other by the snake's body. The fish is no longer in open water. It is inside a narrowing funnel where every movement pushes it closer to contact. This method also reduces risk. Fish with sharp spines or erratic escape behaviors can injure predators during prolonged struggles. By delivering venom quickly and holding securely, sea snakes minimize the duration of contact with an active, resisting animal. Efficiency here is not just about energy. It is about survival. A damaged mouth or broken tooth in a snake that relies on precise strikes can be fatal over time. Evolution has favored a system that ends encounters decisively and with minimal wear. Ecologically, sea snakes play a subtle but important role in reef systems. By targeting fish that shelter deep within cracks and rubble, they influence populations that are less accessible to other predators. This can affect how certain fish species use reef structure, potentially altering grazing patterns and microhabitat dynamics. The presence of a predator that can hunt inside the reef changes how prey distribute themselves, even if encounters are rare. Fear, in ecological terms, reshapes behavior as much as death does. The irony is that despite their efficiency, sea snakes are not aggressive animals. They do not patrol large territories or actively seek confrontation. Their hunting style is opportunistic and precise, built around exploiting moments when prey enters the wrong space. Humans rarely trigger this response because humans are not prey-sized, nor do they move like fish in confined reef corridors. Most dangerous interactions occur when a snake is handled, trapped, or stepped on, situations that force a defensive response. In water, a sea snake's priority is navigation and oxygen management, not engagement. Understanding sea snakes requires abandoning the idea that danger in the ocean always announces itself through size or speed. Their power lies in specialization. They are masters of spaces others cannot use, hunters that turn the reef's most cluttered zones into controlled arenas. Their venom is not a weapon of terror, but a tool of precision, evolved to solve a specific problem. How to stop a fast, flexible animal in a space too tight for a chase. When you watch a sea snake disappear into a crack that looks barely wide enough for its head, it is easy to underestimate what happens next. Inside that darkness, geometry replaces drama. Angles matter. Contact matters. Chemistry matters. By the time prey realizes escape is impossible, the outcome has already been decided. The reef, for all its apparent chaos, has rules, and sea snakes are among the few predators that understand how to use every centimeter of it to their advantage. The seafloor is usually treated as background, a stage on which more obvious actors move and hunt. But in the case of the stonefish, the ground itself becomes the mechanism of danger. Nothing about this animal makes sense if you frame it as a predator waiting to strike. The stonefish is not built around pursuit, reaction time, or aggression. Its power comes from something far more unsettling: the ability to dissolve into the landscape so completely that the environment stops reading as alive at all. What makes encounters with stonefish so devastating is not that they attack, but that people interact with them as if they were part of the reef's architecture rather than a living organism. At first glance, a stonefish does not look hidden. That is the critical misunderstanding. Its body is not tucked behind coral or buried beneath sand. It sits fully exposed on the seafloor, often in plain view, occupying spaces where the eye expects nothing more than rubble, algae-encrusted rock, or broken coral heads. The camouflage works not by concealment, but by misclassification. The human brain scans the reef quickly, sorting shapes into categories, and the stonefish is optimized to fall into the least interesting one possible. It is not read as an animal. It is read as debris. This illusion is achieved through an extreme convergence of texture, color, and stillness. The stonefish's skin is not smooth or streamlined. It is rough, irregular, and covered in wart-like protrusions that mimic encrusting algae, sponge growth, and coral scars. Pigmentation shifts across muted browns, greys, and greens, broken by mottling that mirrors the chaotic patterns of the reef floor. Unlike animals that rely on disruptive coloration to break up their outline, the stonefish relies on continuity. Its surface does not interrupt the visual noise of the environment. It completes it. Stillness is the final and most important element. A stonefish can remain motionless for hours, sometimes days, adjusting only subtly to maintain balance or respiration. In a reef environment where constant motion is the norm, this lack of movement reinforces the illusion of inanimacy. Fish dart, algae sway, sediment drifts, but the stonefish does nothing. It becomes a fixed point in a dynamic system, and paradoxically, that makes it invisible. Motion attracts attention. Absence of motion erases it. This is why people step on stonefish, not because the animal is hidden, but because it is mistaken for something that can be stepped on safely. The danger does not come from surprise lunges or aggressive defense. It comes from trust. A foot placed down in shallow water seeks stability, and the stonefish offers what appears to be a solid, unmoving surface. The interaction is initiated by the human, not the fish, and it is completed through pressure rather than attack. The dorsal spines that define the stonefish's reputation are not weapons in the traditional sense. They are not swung, aimed, or deployed actively. They are structural defenses embedded along the animal's back, each spine connected to venom glands. When pressure is applied, such as the weight of a foot, the spines are forced downward, penetrating the skin and injecting venom deep into tissue. The mechanism is passive but brutally effective. The harder the pressure, the deeper the penetration, and the more venom delivered. This turns a simple step into a full-force envenomation event. The severity of the pain is a direct consequence of this delivery system. Unlike superficial stings or bites, the stonefish injects venom deep into muscle and connective tissue, where it spreads rapidly along nerve pathways. The venom interferes with cellular signaling and causes intense localized damage, triggering pain that is often described as immediate, overwhelming, and radiating. It is not sharp pain alone, but a crushing, expanding sensation that dominates the entire sensory field. Victims frequently report that the pain is so severe it becomes disorienting, disrupting balance, coordination, and rational thought. This is not accidental. The venom evolved to deter predators that might attempt to consume or crush the stonefish, such as large fish or marine mammals. A predator that bites down on a stonefish would experience a rapid, debilitating response, releasing the prey before serious damage could occur. The same system, when triggered by human weight, delivers far more venom than it was ever meant to in a defensive context. The stonefish does not scale its response. The environment applies the force, and the biology responds accordingly. What often goes unnoticed is that the stonefish is also a predator, and a remarkably patient one. It does not chase fish across the reef. It waits. Small fish drifting near the seafloor are funneled by currents, reef contours, and their own foraging behavior into the stonefish's strike zone. When prey comes within range, the stonefish opens its mouth with sudden speed, creating a vacuum that pulls water and prey inward. The strike is over in a fraction of a second, and then the stonefish returns to stillness, digestion beginning without fanfare. In this way, the reef feeds the stonefish deliveries. Currents act as conveyors, moving prey past its position repeatedly. Reef structure channels movement, increasing the likelihood that small fish will pass close enough to be captured. The stonefish does not need to reposition often. Once it selects a productive spot, it can remain there, conserving energy while the environment does the work. This strategy makes sense in nutrient-rich reef systems where prey density is high but unpredictable in movement. The stonefish's metabolic rate reflects this lifestyle. It is not built for sustained activity, but for efficiency. Energy is invested in camouflage, venom production, and rapid strike capability, rather than speed or endurance. This makes the stonefish a low-energy predator, one that thrives by minimizing effort rather than maximizing output. In ecological terms, it occupies a niche that rewards patience over performance. This has broader implications for reef dynamics. By preying on small fish that move along the seafloor, stonefish influence the behavior and distribution of these species. Fish learn, over evolutionary time, to avoid certain textures or shapes, even if they cannot consciously identify the threat. The presence of stonefish contributes to a subtle pressure that shapes how prey use the reef, reinforcing the importance of vigilance near the substrate. Fear, once again, becomes an ecological force. The danger to humans is an unintended consequence of this evolutionary equilibrium. Stonefish did not evolve to harm people, and they do not benefit from doing so. Encounters occur primarily in shallow waters where humans wade, often near shorelines, tidal flats, or reef edges. These are the same environments stonefish favor, not because they seek human presence, but because these areas provide stable substrate, prey traffic, and protection from strong currents. Understanding this shifts the narrative away from fear and toward awareness. The stonefish is not an ambush predator lying in wait to attack. It is a static organism integrated into the reef's physical structure. The risk arises when humans fail to read the environment correctly, treating the seafloor as inert rather than alive. In reef systems, the ground itself can bite, sting, or inject venom, not out of malice, but because evolution has blurred the line between organism and environment. The irony is that the stonefish's success depends on being ignored. The moment it is recognized as an animal, its advantage disappears. Fish avoid it. Predators learn caution, and humans step around it. Its camouflage only works as long as observers accept the reef at face value. Once you understand that the reef is not just a backdrop, but a living system layered with traps, specialists, and passive defenses, the stonefish becomes less mysterious and more logical. Seen this way, the stonefish is not an anomaly, but a lesson. It demonstrates how evolution can weaponize stillness, how danger does not always announce itself through movement or threat displays, and how the most effective defenses are often those that never have to be used intentionally. The seafloor is not neutral ground. It is an active participant in survival. And in the case of the stonefish, it is the trap itself. When you enter shallow reef waters, you are not just swimming above life. You are stepping into a system where rock, algae, and animal merge into a single functional surface. The stonefish occupies that boundary perfectly, a reminder that in the ocean, the difference between landscape and organism is sometimes nothing more than a mistake of perception. At first glance, the lionfish looks like a contradiction drifting through the reef. Its movements are unhurried, almost ceremonial, fins unfurled like decorative fans rather than tools of violence. It does not dart, does not rush, does not surge forward with the urgency most reef predators rely on. In a world where speed often decides survival, the lionfish appears almost indifferent to the chase. And yet, beneath that calm exterior is one of the most spatially intelligent hunting strategies in the reef ecosystem, a method that transforms open water into confinement and motion into inevitability. The lionfish does not need to be fast, because it never allows its prey the space to use speed at all. The reef is a crowded environment, full of visual noise, overlapping structures, and constant movement. Small fish survive here by exploiting gaps, sudden turns, and rapid bursts of acceleration. They are built to flee, not to fight. The lionfish exploits this assumption by changing the geometry of the encounter. Instead of pursuing prey through open water, it advances slowly, extending its elongated fin rays outward and forward, forming a loose but expanding semicircle. These rays are not rigid barriers, but they do not need to be. To a small fish, they represent uncertainty, unfamiliar shapes that disrupt normal escape calculations. The prey begins to retreat, not because it is being chased, but because the space in front of it is becoming uncomfortable to occupy. As the lionfish continues its measured advance, the fin rays spread wider, creating what is effectively a living fence. The prey backs away instinctively, maintaining distance from the strange, radiating shapes, unaware that every retreat reduces its options. The reef itself becomes part of the trap. Coral heads, rocks, and reef walls limit lateral movement, narrowing the available escape routes. The prey is not being pushed into a corner by force, but guided there by its own avoidance behavior. This is the brilliance of the tactic. The lionfish does not control the prey's movements directly. It lets the prey choose its own confinement. From above, the geometry becomes obvious. The prey oscillates backward, adjusting position with small fin flicks, trying to maintain a safe buffer. The lionfish advances just enough to keep that buffer shrinking. The fin rays curve inward, forming a rough arc that closes as the distance decreases. Eventually, the prey reaches a solid boundary, a coral face or rock surface where further retreat is impossible. At this point, the fence becomes a prison. The prey has not been touched, chased, or struck, yet it has nowhere left to go. The final act happens quickly, but only after the space has been fully controlled. Once the prey is pinned against the reef, the lionfish performs a short-range suction strike. The mouth opens suddenly, creating a rapid pressure drop that pulls water and prey inward. There is no dramatic lunge, no extended pursuit. The strike is precise and economical, taking advantage of proximity rather than momentum. In an instant, the prey disappears, and the lionfish resumes its slow, drifting posture, fins still extended as if nothing has happened. This hunting method explains why lionfish appear slow, yet remain devastatingly effective. Speed is outsourced to the environment and the prey's own instincts. The fence does the work. By the time the prey realizes that retreat has become entrapment, it is already within striking distance. In reef systems where structural complexity is high, this strategy is especially powerful. Every coral head becomes a potential backstop, every crevice a dead end. The lionfish does not need to select optimal hunting grounds actively. The reef provides them everywhere. The elongated fin rays that make this strategy possible are also central to the lionfish's defense. Each ray is lined with venomous spines capable of delivering painful stings to would-be predators. These spines are not used offensively during the hunt, but their presence fundamentally changes the lionfish's risk calculus. Many predators learn quickly that attempting to bite or swallow a lionfish results in immediate punishment. The pain and injury inflicted by the spines discourage repeated attempts, effectively granting the lionfish a level of immunity from predation that few reef fish enjoy. This defensive advantage has profound behavioral consequences. Protected by venom, the lionfish can hunt boldly in exposed areas, unconcerned about drawing attention. It can afford to move slowly, to fan its fins widely, to advertise its presence rather than conceal it. Where other predators rely on stealth to avoid becoming prey themselves, the lionfish relies on deterrence. The spines do not just protect the fish physically, they liberate it behaviorally. The combination of bold hunting and effective defense has made lionfish extraordinarily successful, particularly in regions where they are not native. In invasive ranges, local prey species have no evolutionary history with this hunting style. They do not recognize the fin fence as a threat until it is too late. Likewise, native predators do not instinctively avoid the venomous spines, leading to failed predation attempts and painful lessons that may never be fully learned at the population level. The result is an imbalance that favors the lionfish disproportionately. Reproduction compounds this effect. Lionfish reproduce frequently and in large numbers, releasing buoyant egg masses that drift with currents and spread offspring across vast areas. High reproductive output combined with low predation pressure allows populations to expand rapidly. Unlike many reef fish, whose numbers are tightly regulated by predators and competition, lionfish often escape these checks, especially in invaded ecosystems. Their fearless behavior, enabled by venom, allows them to exploit food resources aggressively, reducing populations of small fish that play critical roles in reef health. Ecologically, this has cascading effects. Small reef fish are not just prey, they are grazers, cleaners, and participants in nutrient cycling. Removing them alters algae growth, coral health, and the balance between reef builders and reef eroders. The lionfish, by excelling at a hunting strategy that preys heavily on these species, can reshape entire reef communities. What begins as an individual hunting success scales up into ecosystem-level change. Yet even in their native range, lionfish are remarkable examples of how evolution can favor spatial intelligence over raw athleticism. Their brains and sensory systems are tuned to read the reef as a three-dimensional puzzle, one where angles, distances, and boundaries matter more than speed. Vision plays a role, but so does lateral line sensing, allowing the lionfish to detect subtle water movements generated by prey adjusting position. This feedback helps the predator maintain optimal spacing, advancing just enough to keep the prey retreating without triggering a panicked escape attempt that might slip through the fence. The irony is that the lionfish's elegance can be misleading. Its flowing fins and measured movements give the impression of fragility, even beauty. But this aesthetic softness masks a strategy built on inevitability. Once the fence begins to close, the outcome is rarely in doubt. The prey's own instincts betray it, turning caution into confinement. The reef, normally a sanctuary of hiding places, becomes a wall. Understanding the lionfish requires abandoning the idea that hunting is always about pursuit. Sometimes it is about control. The lionfish does not need to outrun its prey because it reshapes the space around it. It does not need to surprise because it steadily removes alternatives. In doing so, it reveals a deeper truth about predation in complex environments. Success often belongs not to the fastest or strongest, but to the animal that understands geometry best. In the end, the lionfish is both a marvel and a warning. It demonstrates how a single species, armed with effective defense and a clever hunting strategy, can dominate environments unprepared for it. Its prison tactic is not just a way to eat. It is a way to win without rushing, to conquer space rather than bodies. Drifting slowly through the reef, fins spread wide, the lionfish turns the open ocean into a series of closed doors and waits patiently as its prey backs into the only ending available. The reef does not end at its surface. Beneath the coral heads and rock shelves, it opens inward, collapsing into a network of holes, pipes, and crevices that turn open water into a labyrinth of narrow corridors. Light weakens here. Space compresses. Movement becomes restricted not by speed, but by angles. This is the domain of the moray eel, an animal that does not hunt by chasing prey across the reef, but by redesigning the fight around confinement. For a moray, the most important part of the ocean is not where water is free to flow, but where it is forced to narrow. Morays rarely leave these tunnels fully. Their bodies remain anchored deep inside rockwork, coiled and braced like living cables threaded through stone. Only the head protrudes, mouth opening and closing rhythmically. Not in threat, but in respiration. This constant gaping is often misunderstood as aggression, but it is simply how morays move water across their gills in tight spaces. Stillness dominates their posture. They wait, not because they are slow, but because the environment is already doing the work for them. Reef fish move constantly along edges, inspecting cracks for shelter, food, or escape routes. Every hole that looks like safety to a fish looks like a kill space to a moray. The geometry of these spaces defines the outcome before contact is ever made. Small reef fish are agile in open water, capable of sharp turns and explosive acceleration. Inside a crevice, those advantages evaporate. Turning radius becomes limited. Tail beats push water against rock instead of open space. Panic produces noise and vibration that have nowhere to dissipate. The moray eel understands this implicitly. It does not need to patrol or pursue. It only needs to occupy the right doorway. When the strike comes, it is sudden but not expansive. The moray does not launch its entire body forward. It lunges headfirst just far enough to clamp onto the prey, teeth anchoring into flesh or scales with immediate commitment. There is no testing bite. The jaws close once, hard, locking the prey in place. This moment is not about killing yet. It is about control. The moray's long, muscular body remains mostly inside the tunnel, pressed against rock, giving it leverage. The prey, now outside the hole, is suddenly connected to something far heavier than it anticipated. What follows is one of the most unsettling mechanics in reef predation, the backward drag. Instead of pulling prey out into open water, the moray retreats. It reverses, sliding deeper into the hole, drawing the prey toward darkness. This reverses the expected direction of struggle. The prey cannot flee forward because it is being pulled inward. It cannot turn because the tunnel walls restrict movement. The more it thrashes, the more it wedges itself against rock, increasing friction and reducing escape potential. The fight becomes a tug-of-war that only works in one direction. This is where the moray's anatomy reveals its most unusual adaptation. Inside its throat sits a second set of jaws, the pharyngeal jaws. These are not an extra mouth in the dramatic sense often portrayed, but a highly specialized internal structure evolved to solve a specific problem. Most fish use suction to draw prey into the mouth, relying on rapid expansion of the oral cavity. Morays cannot do this effectively inside narrow tunnels. There is no room to generate a strong suction flow. Instead, once the outer jaws secure the prey, the pharyngeal jaws extend forward, grip the prey internally, and pull it deeper into the throat. The motion is efficient, mechanical, and precise, designed for feeding in confined spaces rather than spectacle. The importance of this system is not speed, but inevitability. Once the prey is drawn past a certain point, escape becomes mechanically impossible. The tunnel, the grip, and the internal jaws work together as a single system. The moray does not need venom, crushing force, or repeated bites. Geometry does the killing. The space removes options, and the eel simply capitalizes on that fact. Moray teeth reinforce this strategy. They are sharp, backward curving, and designed to hold rather than slice. Once embedded, they resist outward movement, turning any attempt to pull free into an act that drives the teeth deeper. This makes the backward drag especially effective. Every centimeter the moray retreats increases the prey's disadvantage. Darkness, pressure, and lack of maneuverability combine into a rapidly narrowing margin of survival. The reef amplifies this advantage. Crevices are not uniform tunnels. They twist, branch, and collapse unpredictably. A prey item dragged inside may encounter sudden bends or constrictions that further immobilize it. Even if the moray briefly loosens its grip to reposition, the prey is often already stuck, pinned by its own body against rock. The eel can then re-grip at leisure. What looks like a simple hole from the outside is often a complex internal trap. Morays are not fast swimmers in open water, and they do not need to be. Their muscles are built for sustained force rather than bursts of speed. Anchored against rock, they can exert remarkable pulling power. This is why backing into a moray's hole is so dangerous, not just for fish, but for any animal that intrudes too closely. The fight does not stay outside. It is drawn inward, into a space where the moray has every advantage and the intruder has none. Occasionally, this strategy intersects with another predator's abilities in a way that looks almost deliberate. In some reef systems, morays have been observed hunting cooperatively with groupers. The interaction is simple and efficient. The grouper patrols open water and chases prey toward the reef structure. Fish fleeing the grouper dart into holes and crevices, precisely the spaces morays occupy. The moray, alerted by movement and vibration, intercepts the fleeing prey inside the tunnel. Both predators benefit, and neither needs to communicate explicitly. Geometry and shared opportunity are enough. These partnerships are not constant, nor are they universal, but they demonstrate how specialized hunters can intersect without competition when their niches align. Ecologically, morays occupy a crucial role as gatekeepers of the reef interior. They prey heavily on fish that use holes and crevices as shelter, preventing any single species from monopolizing these spaces. This maintains turnover within reef microhabitats, ensuring that shelter remains dynamic rather than permanently occupied. The fear morays generate also shapes behavior. Fish learn to treat certain holes with caution, altering movement patterns and feeding routes. Even when a moray does not strike, its presence reorganizes traffic along the reef face. Morays themselves are shaped by the thermal and chemical stability of these environments. Crevices buffer temperature fluctuations and reduce exposure to currents, allowing morays to regulate energy expenditure efficiently. Their skin lacks the heavy scales seen in many fish, reducing friction against rock and allowing them to slide through tight spaces without injury. A thick mucus layer protects against abrasion and infection, essential for an animal that spends much of its life pressed against hard surfaces. Despite their fearsome reputation, morays are not reckless predators. They are cautious, calculated, and deeply tied to their chosen shelters. Many individuals remain in the same hole for extended periods, learning the flow patterns, prey traffic, and structural nuances of that specific location. This familiarity increases hunting success. The moray knows exactly how far it can lunge without losing leverage, exactly where the tunnel narrows, exactly how much force is needed to pull prey past critical points. It is not improvising. It is executing a plan refined over time. To witness a moray hunt is to see predation stripped of spectacle and reduced to mechanics. There is no chase sequence, no dramatic collision, no prolonged struggle in open water. There is a sudden clamp, a firm grip, and then disappearance. The reef closes behind the prey as if swallowing it. From the outside, it looks almost anticlimactic. From inside the tunnel, it is absolute. Understanding morays means understanding that danger in the ocean is often directional. The most lethal space is not always in front of you, but behind you. When a moray retreats backward with prey in its jaws, it transforms its shelter into a one-way system. Darkness replaces light. Space collapses. The fight ends not with a blow, but with removal. In the reef, holes are never empty. They are occupied, claimed, and defended by animals that specialize in confinement. The moray eel is the master of this world, a predator that does not need to chase because it owns the exits. Head-first lunge, clamp, backward drag, and silence. The sequence is simple, repeatable, and devastatingly effective. In a place defined by complexity, the moray succeeds by reducing every encounter to a narrow, inescapable line. The seafloor in cold, dim water is not an open plain. It is a compression chamber of shadow, sediment, and silence, where distance collapses and visibility lies to anything that depends on sight. Down here, survival is not decided by speed over long stretches, but by what happens in the final centimeters. This is where the monkfish exists, not as a hunter that moves through the environment, but as an environment that waits. To understand the monkfish, you have to abandon the idea of a predator as something that approaches. The monkfish does not advance. It reveals itself only at the moment when it is already too late. At rest, the monkfish barely resembles an animal at all. Its body is flattened against the seafloor, skin textured like mud, sand, or decaying debris. Coloration varies with substrate, blending mottled browns, greys, and dull greens into a pattern that mirrors the surrounding sediment. Its outline is indistinct, edges softened by skin flaps and irregular contours that dissolve into the background. In the low light of deep or cold waters, where color fades and contrast is minimal, the monkfish is not hidden so much as erased. The brain does not register it as a threat because it barely registers it as a shape. What defines the monkfish is not what you see, but what you miss. The head is enormous, occupying most of the animal's length, and the mouth dominates that head to an almost absurd degree. The jaws stretch wider than the rest of the body seems capable of supporting, lined with inward-pointing teeth designed not to cut, but to prevent escape. This is not a mouth meant for biting pieces off prey. It is a containment device. Functionally, the monkfish is a mouth with a body attached, a trap engineered around the simple principle that anything which enters the opening does not leave. The lure completes the illusion. Extending from the monkfish's head is a modified dorsal spine, tipped with a fleshy appendage that mimics small prey. In the dimness, this lure moves subtly, flicking or waving with just enough motion to stand out against an otherwise still landscape. It does not look like danger, it looks like opportunity. To a small fish or crustacean navigating a low visibility environment, the lure reads as food drifting free of cover, an easy gain in a place where calories are scarce and mistakes are costly. The monkfish does not need to exaggerate the motion. Too much movement would attract suspicion. Instead, the lure pulses gently, just enough to trigger curiosity. The deception works because it aligns perfectly with the sensory limitations of the habitat. In cold and deep sea floors, light penetration is weak, and vision is often grainy at best. Many prey species rely on short-range visual cues combined with lateral line sensing to detect movement and pressure changes. The lure provides a localized stimulus without broadcasting the presence of the predator behind it. There is no large shape approaching, no expanding shadow, no pressure wave announcing an oncoming threat. The monkfish remains still, and stillness is safety in these environments. As prey approaches the lure, the geometry of the encounter tightens. Distance shrinks to a few body lengths, then a few centimeters. At this range, reaction time becomes the limiting factor. Escape reflexes in fish are fast, but they are not instantaneous. They rely on detecting sudden changes in pressure or visual cues that signal an incoming strike. The monkfish bypasses these triggers entirely. It does not rush forward. It does not swing its head. It opens. The opening of the monkfish's mouth is not a bite in the traditional sense. It is a vacuum event. The jaws drop open with explosive speed, and the volume inside the mouth increases dramatically in a fraction of a second. Water rushes in to equalize the pressure difference, carrying the prey with it. This happens faster than most nervous systems can process as danger. There is no time for a coordinated escape response, no opportunity to turn or accelerate. One moment the prey is hovering near the lure, the next, it is gone. The efficiency of this mechanism is terrifying precisely because of its simplicity. The monkfish does not need to aim, it does not need to grab. The physics do the work. Once the prey crosses a critical distance threshold, the suction force overwhelms any swimming effort. Even strong, agile fish are helpless at this range. The teeth lining the jaws angle inward, ensuring that anything pulled inside cannot be expelled by struggling. The trapdoor closes, and the monkfish settles back into stillness, digestion beginning quietly beneath the sediment. This is why prey fails so consistently. In close quarters, speed is irrelevant. Reaction time is the only currency that matters, and the monkfish spends it all at once. By eliminating the approach phase of a typical attack, it removes the window in which prey might recognize danger. The lure does not trigger fear because it is not threatening. The predator does not trigger fear because it does not move. Fear arrives only after the physics have already resolved the encounter. The habitat amplifies this advantage. Monkfish are most common on cold, deep sea floors, where turbidity is high and visibility is low. Sediment clouds easily, further reducing sightlines. In these conditions, mistakes are fatal because there is no room to correct them. A prey animal that misjudges distance or identity at close range cannot simply sprint away into open water. The environment is already constraining movement, and the monkfish exploits that constraint ruthlessly. Energy economics explain why this strategy is so effective. In cold environments, metabolism is slower, and food can be scarce or unpredictable. Chasing prey over long distances would be energetically expensive and inefficient. The monkfish solves this problem by minimizing movement. It invests energy in a single, decisive action rather than prolonged pursuit. Waiting costs almost nothing. Striking costs everything at once, but only when success is nearly guaranteed. This makes the monkfish an energy-efficient predator, perfectly suited to harsh environments. The anatomy supports this lifestyle in every detail. The body is compact and muscular enough to anchor the animal against currents, but not built for sustained swimming. The fins are positioned to stabilize rather than propel. The skin texture reduces reflectivity and breaks up outlines, reinforcing camouflage. Even the coloration adapts over time, matching local substrates to maintain invisibility. The monkfish is not just camouflaged visually, but behaviorally. It behaves like part of the seafloor. Ecologically, monkfish play a role as regulators of benthic and demersal prey populations. They target fish and invertebrates that move close to the substrate, species that might otherwise dominate certain niches. By removing individuals that make poor decisions or take risks, monkfish indirectly shape behavior patterns across the community. Over evolutionary time, this selects for prey that are more cautious near the bottom, altering how energy flows through the ecosystem. There is a grim irony in how the monkfish appears. Its face, wide and flattened, does not resemble the streamlined killers often associated with predation. It looks awkward, even grotesque, as if assembled without concern for aesthetics. Yet this form is the result of extreme specialization. Every exaggeration serves a purpose. The oversized mouth maximizes suction volume. The lure extends the effective reach of the trap. The flattened body reduces visibility and stabilizes the animal against the seafloor. Horror emerges not from malice, but from optimization. The visual rhythm of a monkfish hunt is deceptively simple. A slow, almost hypnotic lure movement. Stillness, stretching into seconds, minutes, sometimes hours. Then an instant vanish. No struggle, no chase. The prey disappears, as if the seafloor itself opened and closed. For observers, the violence feels out of proportion to the motion involved. That imbalance is what makes it unsettling. The monkfish does not announce itself. It edits prey out of existence. Understanding monkfish requires accepting that some predators do not need to be active to be lethal. In environments where visibility is limited and space is compressed, the most dangerous animal is often the one that looks like nothing at all. The monkfish embodies this principle completely. It is not fast. It is not aggressive. It does not dominate through intimidation. It wins by turning patience into inevitability and physics into a weapon. In the cold, dark seafloor where mistakes cannot be undone, The monkfish waits as a living trap. The lure waves. Curiosity closes the distance. The mouth opens, and the environment resets, as if nothing ever happened. On the reef, danger is often associated with movement. Fast silhouettes slicing through blue water, sudden accelerations, bodies built for pursuit. The frogfish breaks that rule so completely that it feels like a glitch in the system. It does not chase. It does not patrol. It does not even swim well enough to pretend otherwise. Instead, it turns stillness into a weapon and proximity into a trigger, compressing the entire act of predation into a distance so short that reaction becomes meaningless. If other reef predators win by closing gaps, the frogfish wins by refusing to let a gap exist at all. At rest, a frogfish is almost impossible to identify as an animal. Its body shape is compact and irregular, more lump than fish, with skin that forms folds, bumps, and filamentous extensions that mimic surrounding sponges, corals, or algae-encrusted rock. Coloration varies wildly, not just between species, but between individuals, shifting across yellows, reds, browns, blacks, and mottled combinations that match local growth exactly. Unlike camouflage that breaks up an outline, frogfish camouflage replaces the outline altogether. There is no clear edge where fish ends and reef begins. To the eye, it is simply another growth attached to the substrate. This illusion works because frogfish do not behave like fish. They do not hover or fin gently in place. They sit. They settle onto the reef and remain motionless for extraordinary lengths of time, adjusting only when necessary to maintain position or respiration. Even their method of locomotion reinforces the disguise. Frogfish rarely swim from place to place. Instead, they walk using modified pectoral fins, stepping slowly across the substrate in a way that resembles drifting debris more than purposeful movement. Every aspect of their behavior reduces the chance of being categorized as a predator. Prey does not approach a frogfish because it is fooled by speed or stealth. It approaches because it never recognizes the frogfish as relevant. Small reef fish navigate constantly around sponges and coral heads, inspecting surfaces for food or shelter, weaving through structures that appear inert. The frogfish relies on this traffic. It positions itself where fish are already moving, embedding its body into the background so completely that passing within striking distance feels safe. That striking distance is the shortest in the reef. Frogfish do not attack from body lengths away. They do not lunge across open space. Their entire strategy is built around letting prey wander to within centimeters of their mouth. This is not a compromise. It is the core advantage. At this range, prey cannot build momentum, cannot turn effectively, and cannot trigger escape reflexes in time to matter. The frogfish does not need to be fast over distance. It only needs to be faster than a blink. The strike itself is one of the most extreme mechanical events in reef predation. Frogfish do not bite in the conventional sense. They deploy a spring-loaded expansion of the mouth that turns the head into a portable vacuum chamber. Muscles and skeletal elements are arranged so that when triggered, the mouth opens at astonishing speed, expanding its volume dramatically in a fraction of a second. Water rushes in to fill the sudden pressure drop, and anything in front of the mouth is carried with it. The prey does not get grabbed. It gets relocated. This suction happens so quickly that even high-speed observation struggles to capture the full sequence clearly. From the prey's perspective, there is no warning phase. There is no visible approach, no shadow sweeping forward, no pressure wave announcing danger. One moment, the environment is static. The next, it collapses inward. The frogfish's head barely appears to move, yet the prey vanishes completely. The entire event can occur faster than the time it takes for neural signals to travel from sensory organs to motor muscles. This is why frogfish attacks are so repeatable and so successful. The energy cost is minimal. The fish does not burn calories chasing or maneuvering. It waits, expends a burst of energy measured in milliseconds, and then returns to stillness. Recovery is rapid, and the mechanics reset almost immediately. In a reef environment where prey density is high but unpredictable, this efficiency is priceless. The frogfish can attempt strikes frequently without significant fatigue. And because each attempt happens at near point-blank range, success rates remain high. Camouflage is what makes this possible. Frogfish often resemble not just generic reef features, but specific organisms like sponges or coral lumps that prey actively approach. Some even grow filamentous skin extensions that sway gently with water movement, reinforcing the illusion of living reef growth. To a small fish, these shapes are familiar and harmless. They do not trigger avoidance behavior. In some cases, prey may even associate these structures with safety, lingering near them longer than they would in open water. The frogfish exploits this learned comfort mercilessly. The irony is that frogfish do possess a lure similar to that of monkfish, a modified dorsal spine that can be waved in front of the mouth to attract prey. But unlike monkfish, which rely heavily on this lure in low visibility environments, frogfish often do not need to use it at all. Their camouflage alone is sufficient. When the lure is used, it adds another layer of misdirection, drawing prey closer to the danger zone without revealing the predator's identity. The lure does not advertise threat. It advertises opportunity. Physiologically, frogfish are built for this lifestyle. Their muscles are arranged to prioritize explosive motion over sustained swimming. Their skeletal structure allows for extreme mouth expansion without damaging tissue. Their metabolism supports long periods of inactivity, punctuated by brief bursts of effort. Even their respiration is adapted to stillness, allowing them to remain motionless without broadcasting their presence through constant fin movement or excessive water displacement. Ecologically, frogfish occupy a niche that rewards precision rather than dominance. They do not outcompete faster predators by taking prey through pursuit. Instead, they remove individuals that make small mistakes, that drift too close, that misclassify danger as background. Over time, this exerts selective pressure on prey species, favoring those that maintain greater distance from ambiguous structures or that react more quickly to sudden environmental changes. In this way, frogfish shape behavior without needing to be abundant or aggressive. Their presence also highlights a broader truth about reef ecosystems. Complexity creates opportunities for ambush. Every sponge, coral head, or rock outcrop introduces visual noise that predators can exploit. Frogfish are specialists in this noise, masters of blending into biological clutter so thoroughly that they cease to exist as separate entities. They are not hidden behind the reef. They are the reef, temporarily given teeth. For observers, the most unsettling aspect of frogfish predation is how little happens on screen. There is no dramatic build-up, no chase sequence to follow. A camera can linger on a frogfish for minutes without capturing anything unusual. Then, without warning, the frame empties. The prey is gone, and the frogfish looks exactly as it did before. This blink and it's gone moment is not just a retention beat for storytelling. It is a faithful representation of reality. Most reef deaths do not announce themselves. They simply occur. Understanding frogfish requires recalibrating expectations about danger and movement. Not all lethal animals advertise their intent through speed or aggression. Some succeed by becoming irrelevant to perception. The frogfish's greatest weapon is not its mouth or its strike, but the way it manipulates attention. By never demanding notice, it ensures that when it finally acts, notice comes too late. In the crowded, colorful chaos of the reef, where life competes loudly for space and light, the frogfish thrives by doing the opposite. It sits, it blends, it waits. And when the distance closes to nothing, when prey drifts into the smallest possible margin of error, the reef itself seems to inhale. Then everything is still again, as if nothing ever happened. From above, the shallow seafloor looks empty. Sand stretches outward in pale ripples, broken only by scattered rocks, faint coral patches, and the occasional shadows sliding across the bottom. To most predators, this is dead space, a place where prey disappears rather than reveals itself. But to a hammerhead shark, the sand is not blank. It is translucent. Every buried movement, every concealed muscle twitch, every faint electrical signal leaking from a living body beneath the sediment registers clearly across a sensory map stretched wide by one of the most unusual head shapes in the ocean. The hammerhead does not hunt what it sees. It hunts what the sand cannot hide. The defining feature of the hammerhead is often reduced to appearance, as if its wide, flattened head were a curiosity or a gimmick. In reality, that shape is a precision instrument. The lateral expansion of the head spreads the shark's sensory organs farther apart than in any other shark, creating an exceptionally broad detection field. Along the underside of the head run hundreds of electroreceptors, the ampullae of Lorenzini, each tuned to detect faint electrical signals produced by muscle contractions and nerve activity. Every living animal leaks electricity. The hammerhead simply reads it better than anything else moving through shallow coastal waters. This wide sensory coverage changes the rules of hunting entirely. Where other sharks rely heavily on vision, smell, or close-range detection, hammerheads scan. They sweep across sandy flats in deliberate arcs, bodies banking smoothly as the head traces overlapping paths just above the seafloor. From this vantage, buried prey becomes visible in a way that defies intuition. A stingray concealed beneath a thin layer of sand may be perfectly camouflaged visually, but it cannot turn off its nervous system. Its heartbeat, gill movements, and subtle muscle adjustments generate electrical signals that radiate upward through the sediment. To the hammerhead, these signals are not noise. They are coordinates. Once detected, the hunt shifts from search to containment. Stingrays are not passive prey. They are powerful swimmers with flexible bodies and strong tails, capable of explosive escape if given space. But the hammerhead understands the geometry of the encounter before it begins. Rather than rushing directly in for a bite, it positions itself to deny escape routes. The shark lowers its head and body, pressing down on the sand above the ray, using mass and leverage to keep the prey pinned. This is not brute force for its own sake. It is mechanical control, turning the seabed into a lid. The head shape that aids detection now becomes a tool of restraint. By spreading its body weight across a wider surface, the hammerhead can apply pressure without needing to bite immediately. The stingray's instinctive response is to flatten further into the sand or attempt to burst free sideways, but the shark's positioning limits those options. Sand plumes erupt as the ray struggles, but the sediment that once concealed it now works against it, collapsing back into place and reducing traction. The environment shifts sides. What was once protection becomes confinement. Only after the prey is controlled does the hammerhead bite. The jaws close with precision rather than frenzy, often targeting the wings or head of the ray to neutralize its movement. This sequence matters. A premature bite risks allowing the ray to escape or strike back with its barbed tail. By pinning first and biting second, the hammerhead minimizes danger and maximizes efficiency. The entire interaction unfolds in close contact with the seafloor, a grounded, methodical process, rather than a dramatic chase. This specialization explains why hammerheads are so closely associated with sandy habitats, shallow coastal regions, and continental shelves. These environments are rich with prey that rely on burial as a primary defense. Rays, flatfish, and other bottom dwellers survive by blending into the substrate, counting on visual predators to pass overhead. Against hammerheads, that strategy fails completely. The shark's sensory system reaches through the sand, making concealment irrelevant. In evolutionary terms, hammerheads occupy a niche defined not by speed or size, but by information. Group behavior adds another layer to this advantage. While hammerheads are often seen alone, certain species form groups, especially during migrations or at specific aggregation sites. In hunting contexts, these groups can create overlapping search patterns that reduce escape options for prey. Multiple sharks sweeping across a sandy flat generate intersecting detection fields, increasing the likelihood that buried animals will be discovered. When prey attempts to flee, it may move directly into another shark's path, turning individual hunts into collective pressure without the need for explicit coordination. This does not mean hammerheads hunt cooperatively in a social sense, sharing prey or strategizing consciously. Rather, their similar movement patterns and shared habitat use produce emergent effects. The sand becomes a grid under constant surveillance. Escape routes shrink as more sensory coverage overlaps. For prey, the effect is the same as facing a coordinated net, even if each shark acts independently. Visually, this hunting style is unmistakable from above. The hammerhead's sweeping turns leave faint trails in disturbed sediment. Sand plumes bloom and dissipate as rays attempt to flee. The shark's body cuts smooth arcs through shallow water, head angled slightly downward, scanning continuously. There is no sudden acceleration, no explosive sprint. The drama comes from inevitability rather than speed. Once detected, the outcome unfolds through control, not pursuit. The hammerhead's success also reflects a balance between sensitivity and specialization. The wide head improves electroreception but comes with trade-offs. Increased drag and altered hydrodynamics mean hammerheads are not built for the same sustained high-speed chases as some other sharks. They do not need to be. Their prey does not flee far. The hunt ends where it begins, on the sand. Ecologically, hammerheads play a critical role in regulating populations of benthic species like rays, which themselves exert strong influence on seafloor communities. Rays feed on invertebrates buried in sediment, and unchecked ray populations can dramatically alter benthic ecosystems. By preying on rays, hammerheads help maintain balance, preventing overexploitation of the seafloor and preserving habitat structure for countless smaller organisms. This cascading effect illustrates how a single sensory adaptation can ripple outward through an ecosystem. Despite their effectiveness, hammerheads are often misunderstood. Their appearance invites exaggeration, their hunting methods framed as brutality rather than specialization. In reality, hammerheads are neither monsters nor indiscriminate killers. They are precision hunters adapted to a very specific problem: how to locate and capture prey that has chosen invisibility as its primary defense. Their behavior is calm, focused, and efficient, shaped by millions of years of interaction with sandy environments. Thermal regulation also plays a role in their habitat use. Shallow coastal waters often provide warmer temperatures that support active metabolism, especially during periods of intense hunting. Hammerheads move between depths and regions seasonally, following prey availability and favorable conditions rather than fixed territories. These migrations connect distant ecosystems, linking coastal flats with deeper offshore zones and reinforcing the hammerhead's role as a mobile regulator rather than a static presence. Understanding hammerheads means reframing the idea of a trap. The shark does not build structures, does not corner prey against walls, does not rely on ambush from concealment. Instead, it turns the environment's assumptions inside out. Sand is supposed to hide. Stillness is supposed to protect. Distance is supposed to offer warning. Against a hammerhead, none of these rules apply. The sand becomes transparent. Stillness broadcasts location. Proximity arrives without notice. Seen this way, the hammerhead is not a creature of chaos, but of order. Its wide head is not an accident of evolution, but a blueprint for reading invisible landscapes. Its hunting behavior is not violence for its own sake, but a demonstration of how sensory superiority reshapes reality. The shark does not terrorize the seafloor. It maps it. As sand plumes settle and the shallow water returns to calm, the hammerhead glides onward, sweeping its head from side to side, reading signals no other predator can fully interpret. Beneath it, the seafloor is no longer a hiding place. It is a ledger of electrical traces, each one a potential meal, each one proof that in the ocean, the most effective traps are not built from coral or teeth, but from perception itself. The water changes long before the shoreline disappears. Blue fades into green, then into a heavy brown that swallows light and distance alike. Sound dulls. Vision collapses to a few body lengths at best. In these places, the ocean feels unfinished, as if it has not yet decided what it wants to be. This is where the bull shark thrives. Not at the edge of visibility, not in open water where speed and spectacle dominate, but in places where certainty dissolves and every movement happens too close for comfort. The bull shark does not wait for prey to make mistakes in predictable environments. It brings danger into spaces where mistakes are unavoidable. Most sharks are creatures of clarity. Their bodies, senses, and hunting styles are tuned to open water or clean coastal seas where silhouettes resolve at distance and escape routes stretch outward in all directions. Bull sharks reject that model entirely. They move upstream into rivers, into estuaries, into flooded deltas where the water carries silt, tannins, and debris. In these systems, visibility is measured in seconds, not meters. Prey cannot see far enough to plan. Humans cannot see far enough to react. The bull shark turns this sensory collapse into its primary advantage. Physiologically, bull sharks are uniquely equipped for this role. They tolerate dramatic changes in salinity, thanks to specialized kidneys and hormonal controls that regulate salt balance in their blood. This allows them to move freely between ocean and fresh water without suffering the cellular stress that would debilitate most marine fish. Rivers are not accidental detours for bull sharks. They are extensions of their hunting grounds. Each transition zone becomes a corridor of opportunity, a place where prey density increases and escape options narrow. Low visibility water does more than hide the shark. It reshapes behavior. Fish in murky systems rely less on vision and more on lateral line sensing, detecting vibrations and pressure changes to navigate and avoid predators. The bull shark exploits this by moving with controlled efficiency, minimizing sudden pressure waves that might alert prey too early. Its approach is not silent, but it is ambiguous. In turbid water, ambiguity is enough. By the time prey resolves the threat, the distance is already gone. This ambush advantage is not about speed in the traditional sense. Bull sharks are powerful swimmers, but their success in these environments comes from timing and positioning rather than raw acceleration. They move along riverbanks, channel edges, and submerged structures where prey naturally congregates. These features act as funnels, guiding fish into predictable paths. When the shark advances, it does so along these same lines, turning the environment into a narrowing corridor rather than an open arena. Rivers and estuaries are not wide-open systems. They are constrained by banks, vegetation, sandbars, and man-made structures. Every bend reduces sightlines. Every narrowing concentrates movement. For prey, these spaces feel safe because they are familiar and productive. For a bull shark, they are ideal. Fewer escape routes mean fewer decisions for the prey to make, and in murky water, hesitation is fatal. The bull shark's broad diet amplifies this advantage. It is not a specialist waiting for a specific prey type or behavior. It is an opportunity predator in the truest sense. Fish, rays, crustaceans, turtles, birds, carrion, and occasionally mammals all fall within its acceptable range. This flexibility removes the need for perfect hunts. The shark does not require ideal conditions or precise timing. Anything that moves incorrectly, lingers too long, or fails to detect the approach becomes viable. This dietary breadth also means bull sharks can remain in river systems longer than many predators. They are not waiting for a single seasonal prey pulse. They adapt to what is available, switching targets as conditions change. In ecological terms, this makes them highly resilient. When one food source declines, another fills the gap. The system itself becomes the menu. From above, a bull shark in a river is almost impossible to spot. Its coloration blends into the sediment-stained water, its outline softened by refraction and debris. From within the water, the experience is even more unsettling. Shapes appear suddenly and vanish just as fast. Distance is compressed. The idea of a warning phase evaporates. There is no dramatic silhouette emerging from blue water. There is only presence, immediate and unavoidable. This unpredictability is what fuels the bull shark's reputation, especially near humans. Beaches near river mouths, estuaries and coastal inlets are places where people assume danger decreases because waves are calmer and visibility appears manageable from above. In reality, these are some of the most complex and deceptive environments in the marine world. Freshwater outflow creates layers of differing density, bending light and distorting perception. Prey species concentrate here. So do bull sharks. The shark does not seek humans, but it does not need to avoid them either. In murky water, identification errors become more likely, and the bull shark's investigative behavior brings it into close proximity. Unlike species that rely heavily on visual confirmation before approaching, bull sharks operate comfortably in sensory uncertainty. They test, assess, and move on quickly. Most encounters end without incident, but the closeness itself is what unsettles. There is no buffer zone. Ecologically, bull sharks play a powerful role as connectors between marine and freshwater systems. By moving nutrients and energy upstream, they link ecosystems that would otherwise remain separated. Their presence influences fish behavior far inland, shaping feeding patterns and habitat use in ways that ripple outward. In some river systems, prey species adjust migration timing or avoid certain areas altogether in response to shark presence. Fear, once again, becomes an organizing force. Thermoregulation also factors into this lifestyle. Rivers and shallow estuaries often warm more quickly than open ocean, supporting active metabolism and digestion. Bull sharks exploit these thermal gradients, moving with seasonal changes to maintain optimal conditions. Their migrations are not rigid routes, but flexible responses to temperature, prey availability, and water flow. This adaptability reinforces their success in dynamic environments where conditions shift rapidly. What makes bull sharks especially effective is not aggression or intelligence in isolation, but integration. Physiology, behavior, and environment align seamlessly. The shark's tolerance for freshwater opens doors. Its sensory systems function despite low visibility. Its diet removes dependency on any single prey type. Its hunting style turns narrow spaces into traps. Each element reinforces the others, creating a predator that feels unpredictable because it refuses to specialize narrowly. Seen this way, the bull shark is not a monster lurking where it does not belong. It is a specialist of uncertainty. It thrives where clarity fails, where borders blur, and where systems overlap. Rivers are not safer versions of the ocean. They are compressed, complicated extensions of it, and the bull shark understands that better than almost any other large predator. As the water darkens and the current carries sediment downstream, the bull shark moves with deliberate calm, following edges invisible to most observers. Prey senses something wrong only at the last moment, when the corridor closes and options vanish. The trap is not hidden beneath sand or behind coral. It is built from geography, from murk, from the simple fact that in these places, there is nowhere far enough away to feel safe. The fear surrounding bull sharks does not come from myth or exaggeration. It comes from proximity, from the knowledge that in water where you cannot see your own feet, something large, powerful, and perfectly adapted to confusion can be closer than you think. Not because it is hunting you, but because it hunts here. The ocean rarely feels small, but when orcas hunt, scale collapses. Space compresses not because of geography, but because of intention. The water itself seems to reorganize, corridors closing, exits dissolving, movement redirected by bodies that understand not just where prey is, but where it will go next. Orcas do not build traps out of coral, sand, or rock. They build them out of motion, memory, and coordination. The trap is not a place. It is a plan unfolding in real time. At the surface, the first sign is often visual. Tall black dorsal fins slicing through blue water in deliberate arcs. Not scattered, not frantic, but arranged. Each fin holds position relative to the others, maintaining spacing that feels intentional even before the behavior becomes obvious. Below the surface, the real structure of the hunt takes shape. Orcas fan out, then converge, adjusting speed and angle with subtle precision. No single individual rushes. No one breaks formation. The group moves like a flexible wall, reshaping itself continuously as conditions change. This is what separates orcas from most predators in the ocean. They are not simply hunting as individuals who happen to be near one another. They are managing prey. The difference is critical. A chase allows for escape if speed, luck, or terrain favors the hunted. Management removes those variables. Orcas reduce choice. They do not force prey forward blindly. They guide it, steering movement with presence, sound, and pressure until every direction leads where the group wants it to go. One of the most iconic examples of this strategy is the bait ball. Schooling fish rely on numbers for protection, compressing into dense spheres to confuse predators and reduce individual risk. Against solitary hunters, this works. Against orcas, it becomes a liability. The pod begins by encircling the school, individuals taking turns diving beneath it and releasing bursts of bubbles or flashing pale undersides upward. These visual and physical cues tighten the ball further, increasing density. The fish respond exactly as evolution trained them to do, drawing closer together in the face of perceived danger, unaware that this response is being exploited. As the bait ball tightens, orcas take turns feeding, lunging through the mass while others hold the perimeter. There is no chaotic rush. Roles rotate. Energy expenditure is shared. The school remains trapped not because it cannot outrun the orcas, but because every direction leads back into the same wall of coordinated bodies. The ocean, which should offer infinite escape routes, becomes a closed system defined by the pod's movement. This same logic appears in hunts that target larger, more dangerous prey. When orcas pursue marine mammals, the goal is not immediate capture. It is isolation. Calves are separated from adults. Individuals are singled out from groups. The pod uses synchronized passes to cut off support, forcing prey into positions where protection disappears. This is especially evident in coastal hunts, where shoreline and open water create natural boundaries. Orcas exploit these edges relentlessly, pressing prey toward beaches or shallow shelves where maneuverability decreases and escape options vanish. In polar regions, the strategy adapts again. Along ice edges, orcas use the environment itself as a tool. By swimming in coordinated lines and generating waves, they can destabilize ice flows, washing seals into the water. Here, the trap is dynamic, combining physical force with timing and positioning. The ice is not broken through brute strength alone, but through understanding how water movement transfers energy. The prey is not chased. It is displaced. What makes these behaviors remarkable is not just their effectiveness, but their variability. Orcas are not a single hunting machine repeated across the globe. Different populations specialize in different prey, and with that specialization comes entirely different strategies. Fish-eating orcas develop techniques optimized for schooling prey. Mammal-hunting orcas refine methods for isolating and exhausting large, dangerous animals. Some populations focus on sharks, targeting them with precision that exploits unique vulnerabilities. These strategies are not instinctive in the narrow sense. They are learned, practiced, and passed down through generations. This cultural transmission is one of the most unsettling aspects of orca intelligence. Young orcas do not simply grow into hunters by trial and error. They learn by watching, participating, and being guided within the pod. Techniques improve over time. Local conditions shape methods. A strategy that works in one region may be absent entirely in another, not because the orcas are incapable of it, but because it was never needed or discovered. Intelligence here is not just problem solving in the moment. It is the accumulation of solutions over decades. The shock factor for prey lies in this management. Orcas do not rely on surprise alone. Even when prey detects them early, escape is rarely straightforward. The pod adapts. If prey turns, the formation shifts. If it accelerates, individuals reposition to intercept rather than chase. The prey is not reacting to a single threat, but to a system that updates continuously. Every attempt to flee feeds new information into the orca's collective response. Communication underpins all of this. Orcas are highly vocal animals, capable of producing a wide range of clicks, whistles, and calls. During hunts, these sounds are often minimized or altered, especially when stealth is required. In other contexts, communication coordinates movement, signaling position, intent, and timing. Sound travels efficiently underwater, allowing orcas to maintain awareness of one another even when visibility is limited. The pod operates as a network, each individual both receiving and transmitting information. This sensory advantage extends beyond hearing. Orcas combine acoustic awareness with keen vision and tactile feedback from water movement. Subtle changes in current, pressure waves from struggling prey, and the movements of podmates all inform split-second decisions. The result is coordination that appears effortless from the surface, but is underpinned by constant sensory integration. Every synchronized turn, Every perfectly timed lunge reflects a shared understanding of the hunt's structure. Ecologically, orcas sit at the top of the marine food web, not simply because they are powerful, but because they are adaptable. Their presence reshapes ecosystems by influencing the behavior of prey species across vast areas. Fish schools alter migration routes. Marine mammals change feeding grounds. Even other predators adjust their habits in response to orca activity. The fear they generate extends beyond direct predation, creating cascading effects that ripple through entire systems. This adaptability also explains why orcas can thrive in environments ranging from polar seas to tropical waters. Thermoregulation is supported by thick blubber layers that retain heat in cold regions, while their ability to move between depths and latitudes allows them to track prey and favorable conditions. Migration patterns are flexible rather than fixed, shaped by learned knowledge of where and when resources become available. The pod remembers. The ocean becomes a map of opportunities. Visually, an orca hunt is unmistakable once it begins. Black fins cut through the surface in deliberate patterns. White eye patches flash as bodies roll and turn. Water churns where coordinated passes intersect. From above, the scene resembles choreography more than chaos. Movements are repeated, refined, adjusted. There is no wasted motion. Even pauses serve a purpose, allowing prey to commit to a direction before the next phase of containment begins. Yet despite this dominance, orcas are not monsters driven by excess violence. They do not kill indiscriminately. They hunt to eat, to teach, and to sustain the pod. The management of prey is not cruelty. It is efficiency evolved in a social predator that depends on cooperation. A failed hunt costs energy for multiple individuals. Success feeds many. Every strategy reflects that balance. Understanding orcas requires abandoning the idea that predation is always a simple contest of speed and strength. In the open ocean, where barriers are rare and distances are vast, the most effective trap is not a physical structure, but intelligence applied collectively. Orcas turn open water into a maze by moving through it together, redefining what counts as an exit and what counts as safety. For prey, the experience is disorienting. The threat is everywhere and nowhere at once. Escape routes appear, then vanish. Pressure builds without a single point of focus. The ocean, once a place of movement and possibility, becomes constrained by intention. This is the true shock of an orca hunt. Not the violence, but the realization that the environment itself has been taken over by a thinking system. As the hunt resolves and the pod regroups, the water settles quickly. The fins drift closer together. Vocalizations return. What moments ago was a coordinated wall dissolves back into individual bodies moving through blue space. The trap disappears as completely as it formed, leaving little evidence behind. The ocean looks open again. But for those who understand what just happened, it is clear that openness was an illusion all along. The ocean does not end at the surface, or even at the continental shelf. It opens downward into a vertical world where light thins, pressure climbs, and space itself becomes the primary obstacle to survival. This is not a place of reefs or shorelines or lateral escape. It is a column, a shaft, a falling corridor that leads away from warmth, oxygen, and sight. The sperm whale does not hunt across this world, it descends into it, and by doing so it turns depth itself into a trap. From above, a sperm whale looks almost blunt, its massive head dominating the front of its body like an anvil pushed through water. At the surface, it moves slowly, conservatively, breathing deeply before committing to what comes next. Then the tail lifts, the body angles downward, and the whale slips beneath the waves, beginning a descent that will take it far beyond where light can follow. Each meter downward strips away familiar sensory cues. Color vanishes first, then contrast, then shape. Eventually, vision becomes irrelevant. For most animals, this would be disorienting. For a sperm whale, this is home territory. The deep ocean is not empty. It is crowded with life adapted to darkness, but it is structured vertically rather than horizontally. Escape does not mean running away. It means going up or down, and both directions come with consequences. Pressure increases rapidly with depth, compressing bodies and altering physiology. Temperature drops. Oxygen availability changes. Animals that live here are finely tuned to specific layers of the water column. Stray too far, too fast, and the body itself becomes a liability. The sperm whale understands this better than any predator alive. Its primary targets, large deep-sea squid, are masters of darkness. They inhabit depths where sunlight has no influence, relying on sensitivity to vibration and faint bioluminescent cues to navigate and hunt. Their bodies are soft and powerful, designed to move efficiently in high-pressure environments. Their arms are lined with suction cups, some rimmed with hardened hooks capable of gripping flesh with astonishing force. Encounters between sperm whales and these squid are not speculative. They are written directly onto the whale's skin. Circular scars, sometimes arranged in patterns along the head and body, mark the places where squid fought back, attaching themselves in desperate resistance. These scars tell a story of endurance rather than ambush. A sperm whale does not rush a squid in a burst of speed. It descends deliberately, using its massive oxygen reserves to stay submerged for extended periods. Its lungs collapse safely under pressure, preventing nitrogen absorption that would cripple most mammals. Blood flow is redirected to essential organs, heart rate slows, energy use is rationed carefully. This physiological control allows the whale to remain calm and functional at depths that would crush or suffocate almost anything else. In this darkness, the whale's most important sense is not sight but sound. Echolocation becomes its primary interface with reality. Powerful clicks are generated within the whale's massive head, focused and projected forward like a beam. These sound pulses travel through water, strike objects, and return as echoes that carry detailed information about shape, size, movement, and texture. To the sperm whale, the deep ocean is not black. It is mapped continuously by sound. This echolocation is not passive. It is active probing, a constant interrogation of space. As the whale descends, it scans the water column ahead, adjusting the intensity and frequency of its clicks depending on distance and target type. When a large squid is detected, the whale shifts from broad scanning to focused tracking. The clicks become more rapid, more precise, locking onto the moving target. The squid, sensitive to vibration, becomes aware of the whale's presence long before physical contact. The hunt begins not with surprise, but with pursuit through darkness. Here, depth itself becomes the trap. A squid attempting to flee has limited options. Moving deeper increases pressure and cold, pushing the squid toward physiological limits. Moving upward reduces pressure but introduces a different problem. As the squid ascends, the change in pressure affects its buoyancy and muscle efficiency. Gas-filled structures behave differently. Tissues experience stress. Speed and coordination can degrade. The sperm whale, built to manage these transitions, maintains pursuit while the squid's body struggles to adapt. Unlike predators that rely on quick kills, the sperm whale engages in drawn-out encounters. The squid fights back, wrapping arms around the whale's head, attaching with suction cups that can hold against tremendous force. The whale's thick skin and blubber absorb some of this grip, but the struggle is real. This is not a clean strike. It is a contest measured in minutes, sometimes longer, unfolding in total darkness where neither animal can rely on vision. Sound, pressure, and touch dominate the interaction. The whale's massive head plays a crucial role here. It is not just a housing for the brain, but a complex acoustic structure that amplifies and directs sound. The shape of the head allows for precise control of echolocation beams, but it also provides a solid platform during physical struggle. When a squid attaches itself, the whale can maneuver, twist, and apply force without risking critical organs. The head becomes both sensor and shield. Eventually, exhaustion favors the whale. The squid's muscles tire, its grip weakens. The whale closes in, using suction to draw the prey inward, swallowing it whole or in large sections. There is no dramatic tearing or display. The victory is quiet, almost anticlimactic, after the prolonged tension of the chase. Then the whale begins its ascent, carrying the remains upward through layers of water that now feel lighter, warmer, and brighter. This hunting strategy shapes the sperm whale's entire life. Migration patterns follow the availability of deep-sea prey rather than surface conditions. Groups move between regions where squid populations are dense, sometimes traveling vast distances to reach productive hunting grounds. Social structure supports this lifestyle. While the deep hunts themselves are often solitary, surface behavior reflects complex social bonds. Communication between individuals allows knowledge of prey locations and environmental conditions to spread through groups over time. Thermoregulation is another critical factor. Deep water is cold, but the whale's thick blubber insulates vital organs, maintaining stable internal temperatures even during prolonged dives. Heat generated by muscular activity is conserved rather than lost, allowing the whale to function efficiently in environments that would sap energy from less adapted animals. This insulation, combined with controlled blood flow, makes repeated deep dives sustainable over a lifetime. Ecologically, sperm whales occupy a unique position. By preying on large squid, they influence deep-sea food webs that are otherwise difficult to observe or understand. Squid themselves are major predators of fish and smaller cephalopods. Regulating their populations has cascading effects that ripple upward through the ecosystem, even reaching surface waters indirectly. The sperm whale acts as a bridge between worlds, transferring energy from the deep abyss to the surface through its own movement and waste, fertilizing upper layers of the ocean in subtle but important ways. The drama of sperm whale hunting lies not in spectacle, but in scale and endurance. There is no audience in the abyss, no light to frame the action. What unfolds there is inferred through scars, behavior, and the occasional glimpse provided by technology. The evidence points consistently to a predator that wins not through speed or surprise, but through patience, sensory mastery, and physiological control. Visually imagining the scene requires abstraction, a massive silhouette moving through black water, pulses of sound radiating outward like invisible beams. A second shape, softer but powerful, reacting, turning, resisting, darkness swallowing everything beyond the immediate interaction. The fight exists almost entirely outside human perception, yet its outcomes shape the lives of some of the largest animals ever to exist. Understanding sperm whales forces a shift in perspective. Predation is not always about corners, walls, or enclosures. Sometimes the trap is vertical. Sometimes escape fails not because there is nowhere to go, but because every direction demands a physiological price. In the deep ocean, depth itself is a weapon, and the sperm whale is the master of wielding it. When the whale finally breaks the surface, exhaling a towering plume of vapor into the air, there is no visible sign of the battle that just ended kilometers below. The ocean closes over the abyss again, silent and opaque. But the scars remain, etched into the whale's body, proof that in the darkest parts of the planet, survival is decided by endurance, adaptation, and the ability to turn the very structure of the ocean against those who live within it. On the reef, violence usually announces itself through motion. A lunge, a chase, a sudden acceleration that signals danger in time for instinct to respond. The mantis shrimp ignores all of that. Its trap does not depend on pursuit, stealth, or deception in the traditional sense. It depends on physics breaking down at a scale where biology is no longer fast enough to matter. The mantis shrimp does not outthink its prey. It outruns reality itself. At first glance, the mantis shrimp looks misplaced among larger predators. It is small, compact, and often brilliantly colored, tucked into burrows in coral rubble or sandy reef flats. It does not patrol the reef. It does not roam. It lives at the threshold between open space and shelter, occupying holes and tunnels that serve as both home and battlefield. From these burrows, it watches, not with the passive patience of ambush predators, but with a constant readiness that turns proximity into inevitability. The defining feature of the mantis shrimp is its raptorial appendages, modified limbs folded beneath the body like compressed springs. These clubs are not muscles extended outward like a punch from a boxer. They are loaded mechanisms, cocked and held under tension by internal structures that store energy. When released, the movement is explosive, snapping forward faster than nerves can transmit warning signals. The distance covered is minimal, often just a few centimeters. But at that scale, speed becomes absolute. This is why prey cannot escape. Reaction time is the limiting factor in almost all predator-prey interactions. Muscles must receive signals, contract, and produce movement. The mantis shrimp's strike completes its action before this chain can even begin. A crab does not see the club coming. A snail does not feel the threat approaching. One moment, armor is intact. The next, it is compromised beyond repair. The physics of the strike push the encounter beyond simple impact. As the club accelerates through water, it moves so fast that the liquid cannot flow smoothly around it. Pressure drops behind the moving surface, and a vapor bubble forms in the wake of the strike. This phenomenon is called cavitation, a process more commonly associated with ship propellers and industrial machinery than living animals. The bubble exists only briefly, but when it collapses, it releases a burst of energy in the form of heat, light, and shock waves. In effect, the mantis shrimp delivers two hits with one motion: the physical impact of the club, followed immediately by the implosion of the cavitation bubble. For prey, this distinction is academic. The result is catastrophic. Shells crack not just from force, but from pressure changes that propagate through material faster than fractures can dissipate. Even when the club does not directly strike a vulnerable point, the secondary shock can finish the job. Armor that evolved to resist crushing jaws or grinding teeth is not designed to withstand localized pressure spikes that behave more like micro-explosions. This is why mantis shrimp specialize in hard-shelled prey. Crabs, snails, and bivalves dominate their diet, animals that rely almost entirely on physical defenses rather than speed. Against most predators, this strategy works. Thick shells deter bites. Hard exteriors slow feeding and increase handling time, making armored prey less attractive targets. Against a mantis shrimp, armor becomes a liability. It provides a rigid surface that transmits shock efficiently, spreading damage inward rather than dissipating it. The encounter often unfolds at the entrance of a burrow. The mantis shrimp does not need to leave its territory to hunt extensively. Its home sits within a rich feeding zone where crustaceans and mollusks move along the substrate. When prey approaches too closely, the mantis shrimp emerges just enough to strike, then retreats immediately. The burrow is both shelter and stage, a narrow doorway where fights are decided in milliseconds. This territorial aspect adds another layer to the mantis shrimp's violence. These animals are fiercely protective of their burrows, which represent safety, mating opportunities, and strategic advantage. Intruders, whether prey or rival mantis shrimp, are met with the same solution: overwhelming force applied instantly. In confrontations between mantis shrimp, the doorway becomes a boundary line, each animal testing the other's willingness to absorb damage. Ritualized displays sometimes precede combat, but when strikes occur, they are delivered with full intent. The small strike distance is critical here. The mantis shrimp does not need room to build momentum. Its weapon is already loaded. This allows it to fight effectively in confined spaces where larger predators would be disadvantaged. Inside a burrow or at its entrance, the mantis shrimp controls geometry completely. The opponent has nowhere to maneuver, nowhere to retreat, and no time to react. From a physiological perspective, the mantis shrimp's entire body is built to survive the forces it generates. The clubs themselves are reinforced with complex internal structures that resist fracture, despite repeated high-impact use. Layered materials within the club distribute stress and prevent catastrophic failure, allowing the appendage to deliver thousands of strikes over its lifetime without shattering. This is a rare example of biological material engineering approaching the limits of what physics allows. Sensory systems support this precision. Mantis shrimp possess highly advanced vision, capable of detecting subtle differences in movement and polarization of light. But in the moment of the strike, vision is almost irrelevant. The timing is pre-calculated. The animal commits to the motion based on proximity and orientation, rather than continuous feedback. Once triggered, the strike cannot be adjusted or stopped. This is commitment predation, where success depends on choosing the right moment, rather than reacting mid-action. Ecologically, mantis shrimp play a significant role in structuring reef communities. By preying heavily on hard-shelled organisms, they influence the distribution and behavior of crabs and snails, which in turn affects grazing pressure and sediment turnover. Burrows maintained by mantis shrimp alter water flow and oxygen penetration in the substrate, creating microhabitats for other organisms. Even their violence has constructive side effects, recycling shell material into fragments that contribute to reef sand. The energy efficiency of this hunting method is deceptive. The strike itself is brief, but reloading the mechanism requires time and metabolic investment. This encourages a strategy of patience rather than constant aggression. The mantis shrimp waits until success is nearly guaranteed before striking, conserving energy for moments when the payoff is high. This balance between explosive force and restraint defines its role as a specialist rather than a brute. For observers, the mantis shrimp's behavior is shocking because it violates intuitive expectations about size and power. Something so small should not be capable of producing such destruction. Yet evolution does not scale linearly. By focusing on a narrow niche and exploiting physical principles rather than biological strength alone, the mantis shrimp achieves effects disproportionate to its size. It is not strong in the way a shark is strong. It is precise in the way a bullet is precise. The visual aftermath tells the story clearly. Shattered shell fragments scattered near a burrow entrance. Cracked carapaces split cleanly rather than crushed. Sometimes prey is left partially intact, the mantis shrimp returning for repeated strikes until access is complete. There is no rush. Once armor is compromised, the outcome is certain. Understanding the mantis shrimp requires recognizing that not all traps are built from environment or behavior. Some are built from fundamental laws. Water is supposed to cushion movement, to slow impacts, to dissipate force. The mantis shrimp weaponizes the moment when water fails to behave like water. In that instant, physics itself becomes hostile. On the reef, where survival often depends on anticipation and avoidance, the mantis shrimp introduces a different rule. Distance is not safety. Armor is not protection. Time is not guaranteed. When a mantis shrimp strikes, there is no warning phase, no escalation, no opportunity to learn from the mistake. The event is over before it can be processed. At the doorway of its burrow, clubs folded and ready, the mantis shrimp waits in a state of compressed violence. The reef moves around it unaware. Then proximity crosses a threshold, the spring releases, water flashes into vapor, and armor fails. When the sediment settles again, the reef continues as if nothing happened, save for the fragments left behind. Physics has spoken, and biology has adapted to listen. In most predator stories, danger moves toward its target. Teeth close distance. Speed decides outcomes. The pufferfish rewrites that logic entirely. It does not ambush, pursue, or corner. It waits until the moment it should already be dead, and then it changes the rules of the encounter so violently that the attack collapses under its own momentum. The trap does not close around prey. It snaps shut around the predator's expectation. In open water, size is destiny. Predators calculate risk based on silhouettes, proportions, and bite mechanics. A fish that fits in the mouth is food. A fish that does not is ignored. The pufferfish survives by exploiting this calculation at the last possible second. It allows the predator to commit, to invest energy, to begin the lunge. Only then does it trigger one of the most extreme defensive transformations in the ocean, turning vulnerability into immediate incompatibility. At rest, a pufferfish looks like a poor candidate for survival. Its body is soft, rounded, and inefficient for sustained swimming. Fins flutter rather than propel. Its movements are hesitant, almost awkward, as if it never evolved past the assumption that speed would solve problems. Bright patterns often cover its skin, contrasting sharply with blue water or reef backgrounds. These colors do not hide it. They announce it. In a world where camouflage is currency, the pufferfish seems reckless. That recklessness is deceptive. The pufferfish lives on timing, not avoidance. It navigates reef edges, seagrass beds, and open shallows where encounters with predators are inevitable. It does not flee at the first sign of danger, because fleeing would expose its weakness immediately. Instead, it delays. It lets predators approach, narrowing the distance until the outcome appears certain. This delay is not ignorance. It is strategy. When the moment comes, inflation begins. The pufferfish gulps water rapidly, forcing it into a highly elastic stomach that can expand to several times its resting volume. This happens in seconds. The transformation is abrupt and startling, even to observers familiar with it. A fish that was small enough to swallow becomes a rigid spherical mass bristling with spines. The mouth that was opening to bite now cannot close around the prey. The attack aborts mid-motion, the predator forced to recoil or reposition, suddenly facing a problem it did not account for. This inflation acts as a panic lock, a last resort mechanism designed to break the geometry of predation. Swallowing predators rely on alignment, on drawing prey headfirst into the mouth. Inflation destroys that alignment instantly. Spines extend outward, increasing effective diameter and adding physical deterrence that can lodge painfully in a predator's mouth or throat. The pufferfish does not need to injure the predator severely. It only needs to make the act of eating impossible. The speed of this response is critical. Predators strike quickly, and hesitation is fatal. Inflation completes before the predator can adjust its bite or redirect force. This is why pufferfish survive encounters that should end them. The decision window for the predator closes faster than it can adapt. Expectation becomes liability. But this defense is not free. Inflation is physiologically expensive and dangerous if misused. Filling the body with water puts immense strain on muscles and organs. It disrupts normal respiration and circulation. The pufferfish cannot remain inflated indefinitely without risking exhaustion, oxygen deprivation, or internal damage. This is why inflation is reserved for moments of extreme threat. It is not a display or a bluff. It is an emergency state. Once inflated, the pufferfish is also less mobile. Its spherical form reduces maneuverability, leaving it vulnerable if the predator persists or if multiple threats are present. The goal is not to fight or chase away danger, but to survive long enough for the predator to disengage. When that happens, the pufferfish slowly expels water, returning to its normal shape and resuming movement. The entire sequence is a gamble that depends on predator behavior and learning. Learning is where the second layer of defense comes into play. Many pufferfish species contain potent toxins in their skin and organs, substances that interfere with nerve function if ingested. These toxins are not delivered through a bite or sting. They are passive, a chemical consequence of consumption. Predators that ignore the physical warning and attempt to eat a pufferfish risk severe poisoning or death. This does not need to happen often to be effective. One failed attempt can imprint avoidance behavior that lasts a lifetime. This creates a feedback loop that favors the pufferfish. Bright coloration becomes a warning rather than camouflage. Predators associate the unusual shape and patterns with danger even before inflation occurs. Over time, this reduces the number of attacks the pufferfish faces. The defense becomes partly preemptive, built on reputation as much as reaction. The pufferfish teaches the ecosystem what not to eat. This combination of mechanical and chemical defense makes the pufferfish a specialist in surviving mistakes. It does not need perfect awareness or flawless judgment. It can afford to be slow, conspicuous, even clumsy, because its response activates after the point where most animals would already be lost. Evolution has placed the defense not at the perimeter of danger, but at the core of it. Ecologically, this has consequences. Predators that learn to avoid pufferfish redirect pressure toward other prey species. This reshapes feeding dynamics within reef and coastal systems. Pufferfish themselves feed on hard-shelled invertebrates, algae, and small organisms, influencing grazing patterns and substrate composition. Their presence alters not just who eats whom, but how risk is distributed across the food web. Thermoregulation and habitat choice support this lifestyle. Pufferfish often inhabit warm, shallow waters, where metabolic processes can support rapid physiological changes like inflation and deflation. These environments also host a wide range of predators, increasing the value of a robust defense system. Seasonal movements may occur as temperatures shift, but pufferfish are generally tied to regions where their defensive strategy is most effective. The visual drama of a pufferfish encounter is unforgettable. A predator closes in, jaws open, movement decisive. Then the prey expands explosively, body swelling into a shape that defies expectation. Spines stand rigid. Colors intensify. The predator veers away, confused or injured, its attack rendered useless by a transformation it could not anticipate. The water settles, and the pufferfish remains, suspended and breathing hard, alive precisely because it did not try to escape. There is a quiet irony here. The pufferfish does not win by being untouchable. It wins by making itself inconvenient. It weaponizes incompatibility rather than aggression. In a system built on efficiency, it survives by breaking efficiency at the worst possible moment for its attacker. This strategy also explains why pufferfish are so visually striking in open water imagery. Their bright colors, odd proportions, and dramatic transformations stand out against blue backgrounds, creating scenes that feel almost unreal. But this aesthetic impact is not incidental. It is part of the warning system. Visibility reinforces memory. Memory reinforces avoidance. The pufferfish benefits from being remembered. Understanding the pufferfish requires a shift in perspective. Not all survival strategies are about dominance, speed, or intelligence in the conventional sense. Some are about refusal. The pufferfish refuses to fit into the predator's plan. It waits until the plan is fully committed, then invalidates it completely. In the open ocean, where mistakes are punished instantly, the pufferfish thrives by turning the moment of greatest vulnerability into a structural problem for its enemy. It does not trap prey. It traps assumptions. And in doing so, it proves that sometimes the most effective defense is not running faster, hiding better, or striking first, but becoming something that simply cannot be eaten. The reef does not always announce danger through movement. Sometimes it announces it through absence, through the way space itself becomes difficult to cross. Sea urchins embody this kind of threat. They do not chase, stalk, or ambush. They wait, rooted in place, turning the substrate beneath them into a field of consequences. The trap they create is not aimed at a single animal or moment. It is structural. Once sea urchins establish themselves, they alter how everything else on the reef must move, feed, and survive. At a distance, a sea urchin looks deceptively simple. A compact body, radiating spines, clinging to rock or wedged into crevices. There is no posture of aggression, no obvious intent. But the closer you get, the more the environment begins to feel constrained. Spines overlap. Shadows thicken. Gaps that once looked passable now demand careful navigation. Predators slow down. Grazers hesitate. The reef floor stops being neutral ground and starts behaving like a minefield. Sea urchins win by forcing caution. Their bodies are immobile, but their defenses extend outward in every direction. Long, rigid spines act as both physical barriers and warning signals, increasing the effective size of the animal far beyond its central body. Approaching a sea urchin is not about speed or strength. It is about angles, timing, and risk assessment. One wrong move can mean a puncture wound, a broken spine lodged in flesh, or infection. For many predators, that risk outweighs the potential reward. This passive dominance reshapes behavior across the reef. Fish adjust their swimming paths to avoid contact. Invertebrates alter foraging routes. Even large animals treat dense urchin zones with respect, skirting their edges rather than crossing directly through. The sea urchin does not need to repel predators actively. It creates an area of denial, a space where movement becomes expensive and mistakes linger. The spines themselves are marvels of functional design. Made of calcium carbonate, they are strong enough to deter bites, yet brittle enough to break off when stressed. This brittleness is not a flaw. A broken spine lodged in a predator's mouth or tissue continues to cause irritation long after the encounter, reinforcing avoidance behavior. Some species add another layer of deterrence through venomous structures associated with their spines or pedicellariae, tiny pincer-like appendages that can deliver painful stings. Not all sea urchins are venomous, but the uncertainty alone amplifies their effectiveness. Predators cannot easily tell which encounters will be merely painful and which might be dangerous. Because sea urchins do not move, their influence accumulates over time. They graze constantly, scraping algae from rock surfaces with specialized mouthparts located on their underside. This grazing is not selective or delicate. It is persistent. Over weeks and months, sea urchins can clear large areas of algae, exposing bare rock and altering the competitive balance of the reef. Algae that once provided shelter or food for other organisms disappear. Coral larvae may find new surfaces to settle, or they may fail entirely if grazing becomes too intense. The sea urchin, by simply feeding, becomes an architect of the ecosystem. This role makes sea urchins ecological gatekeepers. In balanced systems, their grazing helps prevent algae from overwhelming corals, maintaining reef structure and biodiversity. In imbalanced systems, where predators of sea urchins are reduced, their numbers can explode. The result is an urchin-dominated landscape where grazing pressure becomes destructive, stripping reefs down to barren rock. These shifts are not subtle. They redefine which species can live where, which life stages survive, and how energy flows through the system. From the sea urchin's perspective, this is not strategy in the conscious sense. It is consequence. Evolution favored an animal that could survive without fleeing, one that could defend itself so effectively that movement became unnecessary. By anchoring itself to the reef and radiating deterrence outward, the sea urchin turns stillness into power. Predators that rely on quick strikes and decisive bites find no clear entry point. The cost of failure is high, and the reward is uncertain. Some predators have adapted counters, learning how to approach sea urchins without paying the full price. These techniques are rare and specialized, involving patience, manipulation, or exploiting brief moments of vulnerability. Such interactions reveal that even the most effective passive defenses can be challenged, but they do not negate the overall advantage sea urchins hold. For most of the reef community, avoidance remains the safer choice. The visual language of a reef with sea urchins is unmistakable. Spines fill the frame, radiating outward like warning signs. Fish hover at a respectful distance, bodies angled away, ready to retreat rather than advance. The space around an urchin feels charged, even when nothing moves. This tension is the trap. It shapes decisions before they become actions. Sea urchins also illustrate a deeper truth about survival in complex ecosystems. Not all power is dynamic. Some of it is positional. By occupying key surfaces and defending them absolutely, sea urchins influence far more than their own survival. They affect grazing patterns, coral growth, predator movement, and even the physical texture of the reef itself. Their presence changes the battlefield without a single chase or strike. Understanding sea urchins means recognizing that danger does not always arrive. Sometimes it is already there, embedded in the landscape, waiting to punish carelessness rather than reward skill. The reef learns to live around them, adjusting flows of movement and energy to accommodate a creature that refuses to yield space. In this way, sea urchins are not just animals on the reef. They are conditions. Their spines redraw maps. Their grazing rewrites outcomes. They remind us that in the ocean, survival is not always about who moves fastest or strikes hardest, but about who can make themselves impossible to ignore and too costly to challenge. The reef is full of motion that looks purposeful. Fish dart with intention. Predators accelerate, break, and turn with visible logic. Against that constant choreography, the sea anemone appears almost decorative, a soft-bodied organism rooted to stone, its tentacles waving gently as if responding only to water and light. But this stillness is deceptive. The anemone is not passive. It is patient. And patience, in a moving ecosystem, can be a far more effective weapon than speed. A sea anemone does not chase prey because it does not need to. It turns water flow into opportunity. Every tentacle that sways is a sensor and a weapon combined, armed with thousands of microscopic stinging cells that fire on contact. These cells do not seek targets. They wait. When something brushes past, even lightly, the response is automatic and irreversible. The trap closes not through pursuit, but through inevitability. The anemone's tentacles form a living glue trap, but not in the crude sense of adhesive. The sting delivers a rapid chemical and mechanical assault that disrupts nerves and muscles almost instantly in small prey. The victim does not explode into panic or attempt dramatic escape. Instead, movement becomes uncoordinated, then sluggish, then futile. The anemone does not need to overpower prey quickly. It only needs to hold it long enough for time to do the rest. This is where the anemone's feeding mechanics become unsettlingly effective. Once prey is ensnared, nearby tentacles begin to contract, bending inward with slow precision. There is no rush. The prey is transferred hand over hand, tentacle to tentacle, toward the central mouth. This process can take minutes, sometimes longer, depending on the size of the prey. During this time, the prey is alive, aware, and steadily losing options. Escape is not blocked by speed or strength, but by duration. The longer contact is maintained, the less capable the prey becomes of resisting. Time is the true killer here. In a reef ecosystem where most predation is decided in seconds, the anemone stretches the encounter into a prolonged decline. This changes how prey species interact with space. Fish and invertebrates learn through experience or instinct to give anemones a wide berth. Even grazing species that might otherwise feed close to the substrate hesitate near anemone fields. The stinging zone becomes an invisible boundary, reshaping movement patterns without a single chase. Positioning amplifies this effect. Sea anemones do not settle randomly. They anchor themselves in locations where water movement works in their favor, reef edges, channels, and ledges where currents deliver a steady stream of plankton, larvae, and small animals. In these places, the anemone does not wait for prey to arrive by chance. The reef delivers food continuously, like a conveyor belt of drifting life. Each current pulse brings new contact opportunities, each brush against a tentacle another roll of the dice for passing organisms. This positioning also enhances defense. Predators that might otherwise attempt to bite or disturb an anemone are discouraged by the same stinging cells that capture prey. Large fish avoid plunging their faces into tentacle fields, not because the anemone could kill them outright, but because the cost of injury or disorientation is too high. The anemone's territory becomes protected space, a patch of reef that others learn to navigate around rather than through. The stinging cells themselves, known as nematocysts, represent one of the most efficient microweapons in nature. Each is a tiny capsule, containing a coiled harpoon-like structure under immense internal pressure. When triggered, it fires faster than most nervous systems can register, embedding into tissue and delivering toxins that interfere with nerve transmission. This system does not rely on intelligence or choice. It is reflexive, automatic, and relentless. Every tentacle is armed. Every contact carries risk. Yet for all this lethality, the anemone's lifestyle is fragile in its own way. Being rooted means exposure to environmental change. Temperature shifts, sedimentation, pollution, and physical damage from storms can all threaten anemone survival. This is why their placement matters so much. A well-positioned anemone balances exposure to food-rich currents with protection from overwhelming force. Too much flow, and tentacles tear or the animal dislodges. Too little, and food supply dwindles. Thermoregulation plays a role as well. Sea anemones thrive within relatively narrow temperature ranges, relying on stable reef conditions to maintain metabolic function. Sudden changes stress their tissues and disrupt feeding efficiency. Because they cannot move easily, anemones are early indicators of reef health. When conditions deteriorate, their decline signals broader ecosystem trouble long before more mobile species disappear. Despite their apparent simplicity, sea anemones are deeply integrated into reef life. Their presence creates zones of risk and refuge, shaping where organisms choose to live and feed. Small fish may skirt the edges of anemone fields to avoid predators that fear the stings. Invertebrates time movements to avoid peak current flow when tentacles are most active. Even algae growth patterns can be influenced by the grazing pressure redistributed around anemone territories. There is also a paradox at the heart of the anemone's strategy. To be effective, it must remain exposed. Tentacles must wave openly in the current to intercept prey. This openness makes the anemone visible and predictable. Yet predictability does not equal vulnerability when the defense is absolute. Knowing where the danger is does not remove it. It only changes how others behave around it. Visually, an anemone feeding is hypnotic. Tentacles ripple like automated tripwires, responding to water movement rather than intent. When prey makes contact, there is no visible explosion of action, no dramatic snap. The change is subtle. A twitch, a tightening, a gradual inward pull. To an observer, it can look almost gentle. But beneath that softness is a system designed to deny escape through persistence. This contrast between appearance and function is central to the anemone's success. Soft-bodied, colorful, flower-like, it appears out of place among armored, fast-moving reef inhabitants. Predators accustomed to associating danger with speed or size may underestimate it. Prey drifting in currents does not perceive threat until contact occurs. By the time the risk becomes clear, the window for escape has closed. Evolutionarily, this strategy highlights a different path to dominance. The anemone does not win by outcompeting others in movement or strength. It wins by anchoring itself at the right point in the system and letting the system bring prey to it. Energy expenditure is low. Success rates are high. The trade-off is dependence on environmental stability, but in established reefs, that stability can last decades. Understanding sea anemones reframes how we think about predation. Not all traps are sudden. Some are slow, architectural, woven into the flow of life itself. The anemone's trap does not announce itself with violence. It waits quietly, letting currents, habits, and chance do the work. As tentacles continue their endless motion, brushing water molecules aside, the anemone remains fixed, an unmoving center in a constantly shifting world. Around it, fish learn routes, predators learn limits, and prey learns too late. The reef adjusts its behavior accordingly, respecting a creature that does not chase, does not flee, and does not forgive contact. In the end, the sea anemone's power lies not in killing quickly, but in making survival a matter of avoidance rather than escape. It transforms space into consequence and time into a weapon. In a world defined by motion, it proves that stillness, when paired with precision and patience, can be just as lethal. The octopus does not hunt by overpowering the environment. It hunts by rewriting it. Where most predators move through space, the octopus reshapes space itself, turning open water into enclosure, gaps into doors, and freedom into constraint. It is not a trap in the traditional sense. It is an anti-trap, a predator so adaptable that it builds containment wherever it arrives. The reef does not need to provide walls or corridors. The octopus brings its own. At rest, an octopus looks unfinished, a loose collection of arms draped over rock, sand, or coral. Its body has no hard edges, no obvious weapons, no visible signs of dominance. But this softness is precisely what makes it dangerous. Every arm is independent, yet coordinated, capable of gripping, probing, sealing, and sensing. Hundreds of suckers line each limb, tasting and feeling the world simultaneously. The octopus does not approach prey as a single organism. It approaches as a system, spreading outward, mapping escape routes before the prey even realizes it has been detected. When the hunt begins, it does not look like pursuit. The octopus does not chase fish across open water unless forced. Instead, it chooses terrain first. Rocky outcrops, coral heads, crevices, shell beds, and sandy depressions become staging grounds. These are places where prey movement is already limited, where turns are sharper and mistakes more costly. The octopus positions itself so that when it strikes, there is nowhere obvious to go. The pounce is sudden but not explosive in the way a shark's lunge is explosive. It is controlled, precise. The octopus surges forward just enough to close distance, then spreads its arms outward in a living net. Webbing between the arms unfurls, forming a flexible blanket that drops over the prey. This webbing is not rigid. It conforms instantly, sealing gaps and wrapping contours. Water movement slows beneath it. Escape routes vanish, not because they are blocked by walls, but because they are smothered by flesh. Suffocation is the silent killer here. Fish rely on constant water flow across their gills to extract oxygen. The octopus's webbing disrupts that flow immediately. Panic movements only worsen the problem, tangling the prey further as arms tighten and reposition. Suckers lock on, each one a separate anchor point that resists sudden motion. The prey is not bitten right away. It is immobilized, pressed into the substrate or held mid-water under a living blanket until resistance fades. This method is energy efficient and brutally effective. The octopus does not waste effort wrestling. It lets physics and physiology do the work. Oxygen deprivation weakens muscles quickly. Coordination collapses. Only once the prey is fully subdued does the octopus bring its beak into play, delivering a precise bite to begin feeding. The entire process is quiet, controlled, and largely invisible to anything watching from a distance. What makes this hunting strategy exceptional is not just the mechanics, but the decision-making behind it. Octopuses are not reactive predators waiting for chance encounters. They actively select environments that amplify their advantages. A fish caught in open water may still escape. A fish caught against rock or sand has far fewer options. The octopus understands this intuitively. It approaches from angles that cut off retreat, positioning arms to block holes and narrow passages before committing to the strike. This intelligence extends beyond hunting posture into tool-like behavior. Octopuses manipulate objects in their environment with intent. Rocks are shifted to close gaps. Shells are pulled into place to block exits. Debris becomes part of the trap, not as a weapon, but as architecture. These actions are not random. They reflect an understanding of cause and effect, of how altering the environment changes outcomes. The octopus does not simply react to prey behavior, it anticipates it. Sensory adaptations support this flexibility. Each sucker contains chemoreceptors that allow the octopus to taste what it touches, gathering information about prey type, health, and movement. This distributed sensing means the octopus does not need to see everything at once. Its arms explore independently, feeding data back to a central nervous system that integrates touch, taste, and spatial awareness. The result is a predator that can hunt effectively even when visibility is low or obscured by sediment. This brings us to one of the octopus's most famous defensive tools, which doubles as an offensive advantage. Ink is not just a smokescreen for escape. It is a way to reset encounters. When threatened, the octopus releases a cloud of ink that disrupts vision and confuses chemical cues. In defensive situations, this allows retreat. In hunting contexts, it enables risk. An octopus that knows it can vanish at will is free to attempt bolder approaches, probing prey more closely, testing reactions, and committing to strikes that other predators might avoid. This defense-to-offense switch is subtle but powerful. Many predators must weigh every failed attempt carefully, as injury or exposure can be fatal. The octopus, equipped with ink, camouflage, and extreme flexibility, can afford to take chances. If a hunt fails, it disappears into the environment, reappearing elsewhere with minimal cost. This lowers the penalty for experimentation, accelerating learning and refinement of technique over time. Camouflage further blurs the line between defense and attack. Octopuses can alter skin color, texture, and pattern in seconds, blending seamlessly into rock, coral, or sand. This is not passive concealment. It is dynamic deception. As the octopus moves, its skin adjusts to match changing backgrounds, allowing it to approach prey without triggering alarm. By the time the prey notices movement, the octopus is already within striking distance. Ecologically, octopuses exert significant pressure on reef and benthic communities. Their diet includes fish, crustaceans, mollusks, and even other octopuses. This broad prey range, combined with intelligent hunting, makes them influential regulators of local populations. They target animals that hide in crevices, pry open shells, and exploit refuges that many predators cannot access. In doing so, they prevent certain species from dominating sheltered niches, maintaining balance through selective pressure. Thermoregulation and metabolism shape where and how octopuses hunt. Being cold-blooded, their activity levels depend on water temperature. In warmer conditions, metabolism accelerates, supporting more frequent and aggressive hunting. In cooler waters, movements slow, and hunts become more deliberate. Migration patterns are generally limited, but octopuses adjust depth and location seasonally to remain within optimal thermal ranges, following prey availability rather than fixed routes. The visual drama of an octopus hunt is striking when captured at close range. Arms spread wide, webbing unfurling like a net. A sudden cloud of sand as the substrate is disturbed. Prey vanishing beneath a shifting mass of flesh. There is no clear outline to follow, no single point of focus. The octopus becomes the environment, a moving piece of reef that closes around its target. What distinguishes the octopus from other predators in this series is not lethality alone, but adaptability. Where a sea anemone relies on stillness and current, the octopus relies on choice. Where a mantis shrimp commits to a single explosive moment, the octopus adjusts continuously. Where a shark turns space into a corridor through speed, the octopus turns space into a puzzle that only it knows how to solve. This makes the octopus an unsettling presence in the ecosystem. Prey cannot rely on simple rules like distance or cover. Hiding places become liabilities. Open areas offer no guarantee. The octopus does not announce its intent with posture or acceleration. It simply appears where it should not be able to appear. Arms already positioned, exits already sealed. In the end, the octopus represents a different philosophy of predation. It does not trap prey by limiting movement from the outside. It traps prey by becoming the boundary itself. Arms act as doors, nets, and handcuffs. Intelligence selects terrain. Flexibility eliminates predictability. The trap is not fixed in place or time. It is rebuilt for every hunt. As the octopus withdraws after feeding, arms folding back into loose coils, the reef looks unchanged. Rocks remain rocks. Sand settles, but the memory of the encounter lingers in the behavior of those that survive. Routes shift. Hiding spots are abandoned. The environment has been redefined, not permanently, but just long enough for the octopus to eat. In a world where survival often depends on recognizing danger early, the octopus thrives by ensuring that recognition comes too late.